They stand in silence, carved from stone and time. Ancient machines that shouldn't exist. Structures so precise they challenge everything we think we know about the limits of early civilization. Surfaces aligned with near-atomic accuracy, components fitted as if shaped by invisible hands, and designs that feel more like advanced engineering than primitive craftsmanship. Who built them? How were they measured? And what knowledge has history forgotten? These are not myths. These are real mysteries waiting to be uncovered. So sit back, relax, and let's dive into a world where the past looks impossibly advanced. Resting behind glass, its corroded bronze surface barely hints at the precision once hidden within. The Antikythera mechanism appears at first glance like little more than an unremarkable relic pulled from the sea. It was discovered in 1901, scattered among the remains of a Roman-era shipwreck off the rocky coast of the Greek island of Antikythera. For decades, it defied understanding, a lump of metal too damaged to explain itself, too strange to ignore. Only later did its true nature begin to emerge. Beneath layers of mineralized decay lay an intricate system of interlocking gears, many no larger than a coin, some with teeth finer than anything previously known from the ancient world. Dating to around the 1st century BC, the mechanism predates comparable mechanical technology by more than 1,000 years. Its very existence quietly unsettles the established timeline of engineering. As researchers reconstructed its fragments using X-rays and 3D imaging, a complex micro-gear train revealed itself. At least 30 bronze gears worked together in carefully calculated ratios, translating rotational motion into predictive cycles. These were not decorative components. They were mathematical, purposeful, designed to model celestial motion with remarkable accuracy. Mainstream scholarship now widely agrees that the Antikythera mechanism functioned as an astronomical calculator. It could predict eclipses, track planetary movements, and map lunar cycles such as the Metonic and Saros cycles, systems that require a deep understanding of astronomy and mathematics. In essence, it acted as a mechanical representation of the cosmos, operated by hand centuries before the first known mechanical clocks. And yet, questions linger. The gear teeth themselves raise quiet but persistent doubts. Some are cut with a precision approaching tolerances measured in fractions of a millimeter. This level of craftsmanship suggests advanced tools, steady production methods, and a tradition of mechanical knowledge that left almost no other trace. If such expertise existed, where are the workshops, the failed prototypes, the written manuals? Ancient texts mention complex devices. Archimedes is said to have built machines that mimicked the motions of the heavens, and Cicero described bronze spheres that could predict eclipses. These accounts were long dismissed as exaggerations or misunderstood metaphors. The Antikythera mechanism, however, lends them unexpected weight. It suggests that such devices were not only possible, but real. From here, interpretations quietly begin to branch. Some researchers speculate that the mechanism represents the peak of a lost Hellenistic engineering tradition, one that flourished briefly before being erased by war, political upheaval, and the fragility of bronze itself. Others wonder whether this was not a singular marvel, but merely the only survivor of many similar machines, most melted down or corroded beyond recognition. More fringe perspectives go further, asking whether the knowledge embedded in the gear ratios reflects influences we do not yet fully understand. Did ancient astronomers inherit mathematical frameworks from earlier, now forgotten cultures? Were there centers of learning whose records never survived, passing technical wisdom through apprenticeship rather than text? These ideas remain speculative, neither provable nor easily dismissed. What is certain is that the Antikythera mechanism forces a reevaluation of ancient technological limits. It does not shout its mystery. It whispers it through corroded teeth, fractured plates, and incomplete inscriptions. Every new scan answers one question and opens another. Why were certain planets included and others omitted? Was the device educational, ritualistic, navigational, or something more personal? As the microgears continue to be studied, turning silently in digital reconstructions, the mechanism resists final explanation. It exists in a narrow space between what is known and what is suspected, inviting us to reconsider how much ancient knowledge may still lie undiscovered, waiting, like this device once did in darkness, just beyond the edge of certainty. As the microgears of the Antikythera mechanism fade from view, their silent rotations lingering in the mind, the journey continues eastward, away from the Aegean Sea and into a different cultural landscape, where precision took on a more subtle, almost philosophical form. Here, instead of tracking the heavens, ancient engineers sought to master direction itself. In dusty historical records and reconstructed diagrams, the south-pointing chariot appears not as a surviving artifact, but as an idea made mechanical. Imagine a wooden chariot rolling across uneven ground, its wheels turning independently as terrain shifts beneath it. Atop the vehicle stands a small human figure, arm extended, finger pointing steadily toward the south, never wavering, no matter how the chariot turns. No magnets, no stars, just gears. The origins of this device are traditionally traced to ancient China, with early references appearing as far back as the 3rd century BC, though some accounts suggest conceptual predecessors even earlier. Unlike compasses, which rely on Earth's magnetic field, the south-pointing chariot depended entirely on mechanical logic. Its secret lay hidden beneath the platform, a differential gear system capable of translating the relative motion of the wheels into a constant directional reference. At first glance, the concept seems almost counterintuitive. How can a machine know direction without sensing it? The answer, according to mainstream explanations, is that it doesn't, not in the way we understand sensing. Instead, the chariot remembers its orientation. As it moves, the differential calculates changes in rotation between the left and right wheels. When the chariot turns, the gear system compensates, rotating the figure atop the platform by an equal and opposite amount, preserving its original alignment. This principle is strikingly similar to the differential gears used in modern vehicles, technology that would not become commonplace in the West until the 19th century. And yet here it is, described in ancient texts, attributed to engineers such as Ma Jun during the Three Kingdoms period. The implication is difficult to ignore. A sophisticated understanding of relative motion and mechanical feedback existed long before it was thought necessary, or even possible. No complete original chariot has survived. What we have instead are written descriptions, later reconstructions, and scholarly debates over how accurate those reconstructions truly are. Some versions work flawlessly in controlled demonstrations. Others reveal subtle instabilities, suggesting missing details in the historical record. Were the ancient designs more refined than the reconstructions suggest? Or were they symbolic devices, impressive in concept but limited in practice? The mystery deepens when considering the tolerances required for such a system to function reliably. Differential gears demand precise ratios and careful alignment. Even minor errors compound over distance, causing drift. For a south-pointing figure to remain accurate over long journeys, the internal gearing would need to be crafted with exceptional care. This raises an unsettling question. What level of manufacturing precision was truly available at the time? Ancient Chinese metallurgy was advanced, particularly in bronze casting and ironworking. But gear cutting of this nature implies not only skilled hands, but standardized processes, jigs, measurement systems, and a shared mechanical language passed from one generation to the next. Yet, as with the Antikythera mechanism, the broader ecosystem that would support such technology is largely absent from the archaeological record. Some historians propose that the south-pointing chariot was primarily ceremonial or symbolic, used in processions to represent cosmic order or imperial authority. South, after all, held deep philosophical significance in Chinese thought, associated with balance, harmony, and governance. In this view, the machine's purpose was less about navigation and more about demonstrating mastery over natural principles. Others suggest practical applications, guiding armies, mapping terrain, or maintaining orientation during long overland journeys where landmarks were unreliable. But if such devices were widely used, why do they vanish from history, only to reappear centuries later as fragmented descriptions? This absence has invited more speculative interpretations. Some researchers wonder whether the knowledge behind the chariot was intentionally guarded, restricted to court engineers, and lost during periods of political upheaval. Others entertain the possibility that such mechanisms were independently rediscovered multiple times, each iteration refining an idea that never fully entered mainstream technological development. There are even quieter, fringe questions that linger at the edges of academic discussion. Could the south-pointing chariot represent a broader mechanical tradition, one focused not on power or automation, but on balance and relational movement? A tradition where machines were designed to reflect philosophical principles as much as practical ones. If so, how many such devices existed, unrecognized because they did not fit modern categories of technology? Like the Antikythera mechanism, the chariot challenges linear narratives of progress. It suggests that advanced mechanical thinking did not move steadily forward, but appeared in flashes, isolated peaks of understanding that rose, then fell, leaving little trace behind. Each rediscovery forces a recalibration of what ancient engineers were capable of imagining and executing. Today, the south-pointing chariot exists mostly in museums as reconstructions, its gears exposed for modern eyes. When it moves, when the figure atop remains unwavering as the base turns beneath it, the effect is quietly unsettling. There is no spectacle, no noise. Only the calm assertion that someone, long ago, understood motion well enough to make direction obey machinery. And still, the core questions remain unresolved. How accurate were the original chariots over real terrain? How widespread was the knowledge required to build them? And how many other machines, built with similar precision and intent, have vanished entirely, leaving behind only whispers in old texts and the uneasy feeling that the past may have been far more mechanically sophisticated than we are comfortable admitting? As the image of the south-pointing chariot slowly recedes, its gears compensating in silence, preserving direction through pure mechanical balance, the focus shifts once more. From motion and orientation, we move to something more physical, more permanent. From wood and bronze to stone, from devices that traveled across landscapes to marks left behind in the bedrock itself. The plateau of Saqqara lies just south of modern Cairo, stretching out beneath a pale desert sky. It is a place of deep time, where stepped pyramids, burial shafts, and mastabas rise from sand that has swallowed and revealed them again and again. At first glance, Saqqara feels familiar, an extension of ancient Egypt's monumental language of stone and ceremony. But look closer, and certain details resist easy explanation. Scattered among the ruins are granite blocks extracted from quarries hundreds of kilometers away. Granite, one of the hardest natural stones known, demands respect even from modern tools. Embedded within some of these blocks are cylindrical holes, smooth-walled and strikingly precise. In several cases, the cores removed during drilling were left behind, allowing direct study of both the hole and the extracted stone. These are not rough perforations. They are controlled, deliberate cuts. The holes vary in diameter, but many share a defining feature: spiral striations running along their inner walls, consistent and evenly spaced. Under magnification, these marks suggest a continuous rotational cutting action, advancing at a steady rate. Measurements taken in the late 20th century revealed feed rates that appear unusually high, far faster than what would be expected from hand-powered drilling using simple copper tools and sand abrasives, at least according to conventional assumptions. Mainstream Egyptology offers explanations grounded in known ancient techniques. Copper tube drills, combined with abrasive materials such as quartz sand, are thought to have been capable of cutting granite over time. Experimental archaeology has demonstrated that this method can indeed bore holes, given sufficient patience, labor, and skill. The Egyptians were meticulous craftsmen, and time was rarely their enemy. And yet, the details complicate the picture. The uniformity of the drill holes, the apparent consistency of the spiral grooves, and the straightness of the cuts raise questions about control and stabilization. Copper, being relatively soft, deforms easily under stress. Maintaining a perfectly circular, stable drill path through granite would require not only abrasive action, but firm pressure, alignment, and a mechanism to prevent wobble. How was this achieved repeatedly across multiple sites? Some researchers point to the possibility of weighted drilling systems, vertical rigs where mass rather than force drove the cutting action. Others suggest lost variations of bronze alloys or hardened copper tools, optimized through trial and error but never documented in surviving texts. These ideas remain within the boundaries of accepted technological evolution, though the physical evidence continues to test their limits. Then there are interpretations that move further from consensus, though not necessarily into fantasy. Certain engineers and independent researchers have analyzed the striation patterns and proposed that the drill heads may have been more rigid than copper alone would allow. They note that the spiral grooves resemble those left by modern core drills, which rely on consistent rotational speed and stable torque. This does not imply identical technology, but it does raise the possibility of more complex mechanical setups than traditionally imagined. Were these drills turned by teams of workers using coordinated motion, by animal power, or by systems now entirely lost, dismantled, or recycled long ago? No definitive answers survive, and the ancient Egyptians left no clear diagrams of their stoneworking tools at this scale. The mystery deepens when one considers precision. Some granite cores exhibit nearly perfect cylindrical geometry, with minimal deviation along their length. In certain cases, the core appears to have been removed faster than the surrounding stone could fracture naturally, suggesting controlled energy transfer rather than brute force. The stone itself does not lie. It records every vibration, every hesitation of the tool that shaped it. And yet, the builders remain silent. There is no single inscription explaining the process. No tomb relief clearly depicting a granite core drill in operation. What we have instead are results, stone surfaces bearing the memory of contact, pressure, and motion. They speak indirectly, asking us to infer the method from the mark. As with the Antikythera mechanism and the south-pointing Chariot, the Saqqara drill holes occupy an uncomfortable space between established history and unanswered possibility. They do not demand a radical rewriting of the past, but they do require flexibility. They suggest that ancient engineering may have reached levels of refinement that were rare, specialized, and perhaps limited to small groups of skilled practitioners. Some historians argue that we underestimate what sustained craftsmanship can achieve without modern power. Others caution against projecting contemporary expectations backward, reminding us that efficiency and precision can arise from methods that look primitive only because we no longer practice them. Still, questions persist. Why are such drill marks not more widespread? Were these techniques reserved for elite projects, experimental phases, or symbolic constructions meant to demonstrate mastery over stone itself? And if such precision was achievable, what other tools might have existed, used briefly, then lost to time? Standing at Saqqara, the desert wind moving softly over cut granite, the drill holes do not announce their mystery loudly. They wait. They invite close attention, careful measurement, and restraint. They remind us that history is not only written in texts and monuments, but etched into materials, sometimes at scales so fine they border on the limits of perception. And as we follow these marks deeper into the stone, one question lingers quietly beneath them all. How much of ancient engineering knowledge has truly been forgotten? And how much is still there, patiently preserved, waiting for us to learn how to read it? As the granite of Saqqara fades into memory, its drill marks lingering like frozen motion in stone, the focus subtly shifts once again. From tools that cut into the earth itself, we move toward devices that sought to understand the sky. From marks left behind in matter to mechanisms designed to mirror the order of the heavens. The questions remain the same, only the scale changes. Imagine entering a quiet courtyard in ancient Greece, perhaps in Athens or on the island of Rhodes. Bronze glints softly in lamplight. Before you stands a compact mechanical assembly, rings, shafts, and rotating elements arranged with deliberate symmetry. When set in motion, it does not lift stone or carve rock. Instead, it moves the planets. Long before the Antikythera mechanism astonished modern researchers, ancient Greek thinkers were already obsessed with celestial order. The sky was not a backdrop. It was a system, predictable, mathematical, and worthy of imitation. Philosophers, astronomers, and engineers worked together to translate observation into form and theory into mechanism. Written sources offer tantalizing glimpses. Plato and Aristotle described the heavens as nested spheres, each carrying a celestial body in precise, eternal motion. But it was later figures, Archimedes, Eudoxus, Hipparchus, who appear to have pushed these ideas into the physical world. Cicero, writing in the 1st century BC, described seeing a device attributed to Archimedes, a bronze sphere that reproduced the movements of the sun, moon, and planets with uncanny accuracy. When turned by hand, it displayed eclipses, cycles, and alignments as they appeared in the sky. No such device survives. What remains are descriptions, fragments of admiration preserved in text, written centuries after the machines themselves were constructed. To some scholars, these accounts represent theoretical models or teaching aids exaggerated by later authors. To others, they suggest something more concrete. Fully realized planetary orreries, mechanical systems capable of simulating complex celestial motion long before such devices were thought feasible. The challenge lies in the planets themselves. Unlike the sun and moon, which move with relative regularity, the visible planets exhibit retrograde motion, loops and reversals that baffled observers for centuries. Accurately modeling these paths requires layered motion, variable speeds, and carefully calculated ratios. In modern terms, it demands a sophisticated gear system. Could ancient Greek engineers have achieved this? Mainstream scholarship acknowledges that Greek mathematics was more than capable. Geometric models such as epicycles and deferents were well established by the 3rd century BC. What remains debated is whether these abstractions were translated into physical mechanisms before the Antikythera device. Some historians argue that early planetary models existed only as diagrams or thought experiments. Others point out that the Greeks were not strangers to complex machinery. Water clocks, automata, and theatrical devices powered by gears and weights were already part of their technological vocabulary. The absence of surviving examples complicates everything. Bronze was valuable. When devices broke or fell out of use, they were melted down. Wood decayed. Iron rusted. What survives is not necessarily what once existed, but what escaped reuse and corrosion. Still, certain clues persist. Fragments of gear-like components have been found at Hellenistic sites, their functions uncertain. Ancient texts reference spheres and globes that move according to fixed laws. Some descriptions hint at devices that were not merely symbolic, but operational, capable of prediction, not just demonstration. And then there is the Antikythera mechanism itself, emerging suddenly in the archaeological record with no clear lineage, as though it appeared fully formed. This abruptness has fueled speculation. One line of thought suggests that Antikythera represents the endpoint of a long, largely invisible tradition of mechanical astronomy. Earlier orreries may have been simpler, less precise, or built in limited numbers for elite patrons and scholars. Over generations, incremental improvements could have culminated in the device recovered from the sea. If so, Antikythera is not an anomaly, but a survivor. More speculative perspectives wonder whether some Greek planetary devices were far more advanced than typically assumed, perhaps incorporating differential motion, variable gearing, or even feedback mechanisms. These ideas remain unproven, but they are not entirely disconnected from known capabilities. After all, similar principles appear in later Greek engineering texts, though often stripped of their original context. There is also the question of intent. Were these devices scientific instruments designed to test and refine astronomical theories? Were they educational tools used to teach students the harmony of the cosmos? Or were they philosophical objects, mechanical expressions of order meant to embody the belief that the universe itself was governed by reason and proportion? In ancient Greek thought, the boundary between science, philosophy, and craftsmanship was fluid. To build a working model of the cosmos was not merely technical, it was intellectual, even spiritual. A device that could mirror planetary motion was a statement that the universe could be understood and that human hands could replicate its logic. And yet, the machines are gone. We are left reconstructing shadows from words, inferring mechanisms from metaphors, and testing hypotheses against a single extraordinary artifact found centuries later. Each new insight into the Antikythera mechanism raises the same quiet question: how many earlier devices must have existed for such knowledge to be refined? As with the granite drill marks of Saqqara and the silent gears of the south-pointing Chariot, the Pre-Antikythera orreries refuse to fully resolve themselves. They sit at the intersection of certainty and loss, reminding us that history is not a complete record, but a fragmentary one. Somewhere between the stars described in ancient texts and the machines we can no longer see, there is a gap, a space where knowledge once lived, worked, and moved. Whether those early planetary devices were rare marvels or part of a broader, forgotten tradition remains an open question. And as we continue to uncover traces of precision where we least expect it, one wonders how many other mechanisms, built to measure, model, and understand the universe, still lie beyond our reach, waiting to be rediscovered not in ruins, but in the careful rereading of the past. As the image of Greek orreries fades, their silent rotations tracing imagined planets through bronze and wood, our journey returns to the Earth, but not to monuments or quarries. Instead, we turn to the subtle precision of human hands, to a different kind of mechanism. One designed not to measure the heavens, but to harness force with unparalleled efficiency. The Qin dynasty in ancient China offers a window into this world, a civilization not only focused on empire and ceremony, but on engineering that could be measured, replicated, and deployed with deadly consistency. Imagine standing in a quiet workshop within the sprawling Qin capital, perhaps beneath the shadow of the early city walls, where artisans and soldiers converge in purpose. On a workbench lies a crossbow, deceptively simple at first glance. But here, hidden within its wooden stock, is a mechanism that demands careful study, a trigger system so modular, so precise, that it could be disassembled and reassembled with interchangeable parts. The idea of interchangeable components seems modern, but in this case, it was very real over 2,000 years ago. The earliest surviving references to these devices appear in texts from the 4th to 3rd centuries BC, during the Warring States period, with widespread adoption under the Qin dynasty, beginning in 221 BC. Archaeological excavations at sites such as the Terracotta Army have yielded hundreds of bronze crossbow triggers and stocks, some remarkably uniform, suggesting a standardization rarely seen in any contemporaneous weaponry. The precision is astonishing. Pins, levers, and sears were designed to function consistently, even after repeated assembly, disassembly, or long-term use. The tolerances required are subtle, yet critical. Too loose, and the mechanism misfires. Too tight, and it becomes unusable. Modern experiments with reconstructed Qin crossbows highlight the sophistication of these designs. A single soldier could swap a trigger assembly in moments, restoring a weapon to full operation in the field. But achieving this requires not only careful measurement, but knowledge of material properties, metallurgy, and mechanical leverage. Bronze components must resist wear, fit together seamlessly, and transfer force predictably. The more one studies these mechanisms, the more they resemble small-scale engineering marvels rather than simple military implements. Mainstream scholarship often attributes these innovations to practical necessity. The Qin army was vast, and uniform weapon systems simplified logistics and maintenance. Standardized triggers allowed for rapid repair and mass production, ensuring that every soldier could rely on a crossbow that functioned identically to another. It was an early example of what modern engineers would call interchangeable parts, a concept later celebrated in the industrial age. And yet, deeper questions emerge. The tolerances observed in surviving triggers are strikingly fine. Were such components truly mass-produced to the same precision across the empire? Did artisans employ jigs, templates, or other unseen tools to achieve consistency? Or were these mechanisms refined individually through the skill and experience of master craftsmen? The historical record is silent, leaving only the physical evidence to hint at possibilities. Some historians suggest that the Qin's standardization represents more than military pragmatism. It reflects a sophisticated understanding of mechanical principles. The trigger assembly is effectively a compact machine, translating stored energy from the drawn bowstring into controlled, repeatable motion. Achieving consistent performance requires awareness of friction, leverage, spring tension, and the interaction of multiple moving parts. To modernize, it borders on engineering at a micro scale. Others entertain more speculative interpretations. Could the apparent uniformity imply an unrecorded workshop methodology, a system of quality control and measurement lost to history? Were the techniques taught systematically across the empire, or preserved within select artisan families, carefully guarded to maintain military advantage? If so, what knowledge accompanied these methods? Mathematical tables, measuring devices, or unrecorded procedures that allowed craftsmen to produce near-identical mechanical parts without the tools we take for granted today? Further intrigue arises when considering the longevity and adaptability of these mechanisms. Some triggers show evidence of repair, modification, or incremental improvement. Did soldiers themselves carry spares, or were workshops established to maintain stocks across the empire? The Qin military seems to have anticipated logistical challenges centuries ahead of widespread mechanized armies, hinting at a level of organizational and technical foresight that remains remarkable. And yet, as with so many ancient machines, the full story is missing. Only fragments survive, often corroded or incomplete. We can reconstruct motion, measure dimensions, and hypothesize methods, but we cannot observe the hands that made them. We can admire their precision, wonder at the ingenuity, and speculate on lost techniques, but the complete methodology remains elusive, hidden within the impermanent records of time. Standing over these triggers, one cannot help but reflect on the scale of knowledge embedded in what seems outwardly simple. They are small devices, yet they encode ideas about motion, force, standardization, and durability. They demonstrate a quiet sophistication, a form of ancient engineering that bridges philosophy and practicality, theory and hands-on craft. And as with the south-pointing chariot, the Antikythera mechanism, and the granite cores of Saqqara, they remind us that human ingenuity often far exceeds the surviving evidence of its work. Ultimately, the Qin Dynasty crossbow trigger invites reflection not only on precision, but on loss. How many other mechanical innovations, refined and replicated across vast territories, have vanished entirely? What other mechanisms existed that combined practical function with subtle engineering sophistication, leaving only traces for us to ponder millennia later? And perhaps most tantalizing, what principles, once known and now forgotten, could still be rediscovered if we read carefully enough between the lines of history and the metal left behind? As the precision of Qin crossbow triggers slowly recedes into memory, metallic levers and modular parts designed to channel human force with subtle efficiency, our exploration returns once more to stone. Not for structure, not for fortification, but for form itself, for objects that seem simple at first glance, yet conceal layers of calculation, craftsmanship, and mystery. The deserts of Egypt, with their sun-bleached sands and timeless monuments, are home to one of the most confounding examples. Hard stone vessels, shaped with a symmetry that continues to astonish modern observers. Step into a museum gallery or a quiet storeroom where artifacts are preserved behind glass. Here lie bowls, jars, and vases carved from granite, diorite, basalt, and other exceptionally hard stones. Their surfaces are smooth to the touch, their edges uniform, and their symmetry so exact that even modern tools struggle to replicate it without painstaking effort. Some vessels are perfectly circular in cross-section, with walls of even thickness, tolerances measured in fractions of a millimeter. Others reveal interiors that mirror the exterior almost flawlessly, a reflection of balance, proportion, and control that seems almost uncanny. These vessels date as far back as the Old Kingdom, around 2600 BC, yet their precision implies techniques far beyond what surviving records suggest. The Egyptians left no instruction manuals for achieving such perfection. No treatises describe how to hold a tool steady against granite harder than most metals, or how to grind and polish a cavity so smoothly that it could contain water without leakage. Yet these objects exist, tangible proof that such knowledge was attained. Mainstream archaeology often attributes the creation of these vessels to patient abrasion. Workers would use harder stones, sand, and repeated motion to gradually hollow out the interior. Experiments confirm that such methods could, given enough time and skill, produce impressive results. But time alone does not explain every observation. Many vessels exhibit rotational symmetry that would require consistent angular motion maintained over long periods, a challenge even today. Small variations in force, angle, or motion would produce noticeable asymmetry, yet the ancient examples show none. Moreover, the finish itself raises questions. Some interiors are polished to a mirror-like sheen, almost as if they had been turned on a lathe. The surfaces are uniform, not only in smoothness, but in curvature, suggesting careful measurement and control. Did the Egyptians employ some form of rotational machining system? If so, how did it function in an age before metal lathes or standardized bearings? The tools and techniques remain speculative, tantalizingly out of reach of direct observation. The mystery deepens when one considers scale. Some vessels are small enough to be held in a single hand, yet others are massive, weighing tens of kilograms. Both categories share a similar precision. Achieving identical tolerances across varying sizes implies either an advanced understanding of proportional scaling or remarkably consistent technique applied over generations. Could workshops have maintained standards across multiple artisans? Were there master craftsmen whose methods were meticulously preserved, then transmitted to apprentices who could replicate precision without written instruction? Some researchers propose mechanical aids. Simple wooden jigs, rotating platforms, and corded mechanisms might have been used to maintain alignment. Yet no surviving examples exist to confirm this. Others point to the possibility of lost techniques, hints of tools or processes that have vanished entirely, leaving only the results behind. In this sense, the vessels themselves are the only witnesses, speaking silently of methods and knowledge that remain hidden from us. Even more intriguing are examples where symmetry approaches what we might call atomic-level accuracy, not in the literal sense of modern engineering, but in the astonishing consistency of curvature, wall thickness, and finish. In some cases, a vessel could be spun or rotated, and its reflections suggest a precision that seems almost deliberate in a way that borders on mathematical intention. Were these objects utilitarian, ceremonial, or symbolic? Perhaps all three. Perhaps their perfection was meant to reflect cosmic order, mirroring the Egyptians' belief in balance, harmony, and ma'at, the principle of universal equilibrium. And yet the techniques remain elusive. Hard stone vessels are often found in tombs and temples, isolated from workshops. Unlike pottery or metalwork, they do not survive in large numbers. Each example hints at a level of technological sophistication that is tantalizing yet fragmentary. What principles guided the craftsman? How much experimentation, observation, and iteration was required to achieve such results? Did the process involve tools lost to time, or knowledge transmitted orally and refined through practice? Standing before these objects, one senses both awe and quiet frustration. The vessels do not boast. They do not speak in words or diagrams. Instead, they offer a measured, patient testimony to skill, patience, and understanding. They challenge assumptions about what is possible with simple materials, and they remind us that ancient engineering was not always about size or spectacle, but about control, precision, and mastery over the material world. Like the south-pointing Chariot, the Antikythera mechanism, and the chin crossbow triggers, these hard stone vessels occupy a threshold between known and unknown. They are evidence of a lost chapter in technological history, machines of subtlety rather than scale, designed not to move armies or chart the heavens, but to manifest an almost imperceptible perfection in stone. And so, as we trace our eyes along polished curves, examine mirrored interiors, and wonder at the symmetry that survives thousands of years, one question lingers inescapably. How much more knowledge has vanished, preserved only in objects that seem simple, yet hide extraordinary skill? What other mechanisms, mechanical, rotational, or otherwise, might once have existed, now lost to time, leaving only the enduring proof of their ingenuity in the vessels we can still hold and contemplate? As the smooth, mirrored surfaces of Egyptian hardstone vessels fade from view and the silent testimony of rotational perfection lingers in our minds, our journey returns once more to the heavens, but this time, not through a single device, not through a preserved artifact like the Antikythera mechanism, but through the tantalizing whispers of machines that may have existed, now lost to time. We are entering the world of Hellenistic astronomical gear calculators, mechanical systems described in texts, hinted at in sketches, yet absent from the archaeological record. Picture a workshop somewhere in the Mediterranean, perhaps in Rhodes, Pergamon, or Alexandria, between the 3rd and 2nd centuries BC. Sunlight filters through tall windows, illuminating tables strewn with bronze gears, wooden shafts, and fragments of parchment covered in mathematical symbols. Here, scholars, mathematicians, and artisans may have collaborated, their goal not simply to understand the cosmos, but to replicate it mechanically. Imagine turning a small handle and seeing the planets trace their paths across the firmament, a miniature universe moving in calculated harmony. The most famous survivor of this tradition, of course, is the Antikythera mechanism, recovered from a shipwreck in the early 20th century. Yet the texts of Cicero, Archimedes, and later writers hint at a broader array of devices: spheres that reproduce eclipses, machines that show planetary positions, and counters of the heavens that never err. Were these purely theoretical constructs, as some scholars contend? Or were there fully functional calculators, each with its own configuration, its own precision, now lost to the corrosion of time and the recycling of metal? We know that the Hellenistic world was obsessed with harmonics, proportions, and the mathematical description of motion. Epicycles, deferents, and eccentric orbits were not merely abstractions. They were the language in which scholars described celestial regularity. Translating these complex calculations into a working mechanism would require a level of precision that borders on extraordinary. Every gear ratio, every differential arrangement had to be exact. A single misalignment could disrupt the representation of months, years, and planetary cycles. Evidence for lost variance is fragmentary but compelling. Literary references speak of devices that could predict lunar and solar eclipses decades in advance. Some texts suggest planetary models more sophisticated than the Antikythera itself, perhaps incorporating mechanisms to account for retrograde motion in more planets, or to reconcile differing observational traditions from Babylonian and Greek sources. The precise configuration of these machines is unknown, but the repeated mention across multiple sources suggests that the Antikythera mechanism may have been only one example of a broader tradition. Archaeologists have identified bronze gear remnants at Hellenistic sites that do not match known artifacts. Could these be fragments of earlier or parallel machines? Some scholars have proposed that these lost calculators may have varied in scale and function, some designed for teaching, others for courtly display, and perhaps a few for scientific prediction. If true, the Hellenistic world may have supported a small network of mechanical astronomers, building and refining devices across centuries, each innovation building on the last, until the knowledge was abruptly interrupted by war, decay, or the disappearance of patronage. The precision implied is remarkable. For gears to model celestial motion accurately, artisans would need to cut teeth at specific angles, with spacing precise to fractions of a millimeter. Bearings or bushings would need to reduce friction without modern lubricants. Axles would need to be true, and rotation smooth, even under sustained use. The Antikythera mechanism shows us that this was achievable, but it also invites a broader question. How many other machines reached similar levels of sophistication, only to vanish entirely? Speculative perspectives deepen the mystery. Some researchers suggest that the lost variants may have included multiple layers of gearing designed for modularity, enabling calculation of phenomena not preserved in the surviving device. Others wonder whether certain calculators incorporated innovations that anticipated concepts only formally described much later, such as differential motion or epicyclic gearing applied to multiple axes simultaneously. While these ideas cannot be confirmed, the sophistication of the Antikythera mechanism itself lends them plausibility, or at least plausibility worth considering. Chariot. And yet, every answer we propose exposes another gap. What became of these machines? Why did this knowledge not survive the collapse of Hellenistic kingdoms? Was it preserved in Alexandria only to be lost in fires, or dispersed among scholars whose manuscripts decayed in obscurity? The gear fragments, textual references, and reconstructed mechanisms leave only tantalizing glimpses of a tradition that may have been richer, more varied, and far more sophisticated than a single artifact can convey. What remains certain is the legacy of ingenuity. These machines demonstrate that human understanding of the cosmos was not limited to observation and mathematics. It extended into physical construction, into the tangible realm of gears and levers. They illustrate a Hellenistic willingness to translate abstract theory into practical mechanical form, a willingness that echoes across millennia, from bronze spheres to modern computational devices. And yet, as we trace the outline of these lost calculators in imagination and scholarship, a quiet question persists. How many devices, more precise, more complex, and perhaps more astonishing than the Antikythera mechanism itself, were once turning silently in workshops and palaces, only to vanish without a trace? How much knowledge of planetary motion and mechanical replication was lost to history, leaving us with fragments, hints, and shadows of what was once a flourishing mechanical tradition? The Hellenistic astronomical gear calculators remind us, once again, that history is not always linear. Knowledge can emerge, flourish, and vanish, leaving only subtle evidence for those patient enough to study it. And as we continue to piece together the fragments of this lost mechanical world, one is left to wonder, what other wonders of precision, hidden in plain sight or buried beneath centuries of time, are still waiting to be rediscovered? As the images of lost Hellenistic astronomical calculators fade into the mind, their delicate bronze gears and invisible hands still tracing the movements of stars, our exploration returns to the Earth, but to motion and force rather than the heavens. From miniature planetary machines, we now turn to devices that manipulated massive weight, harnessing precision to move stone and timber with astonishing efficiency. The Roman cranes and their ball-bearing rotational assemblies. Here, in the ruins of ports, amphitheaters, and temples, a quiet sophistication endures, encoded in bronze, iron, and wood. Imagine standing at the edge of a bustling Roman harbor around the 1st century BC. Ships unload marble blocks, timber, and cargo of every kind. Amid the clamor, cranes rise above the docks, towering wooden frameworks, pulleys swinging with heavy loads, counterweights calibrated to perfection. Their purpose seems obvious, lifting stone, loading ships, but closer inspection reveals a subtlety often overlooked. Some surviving components, preserved in stone channels or described in Vitruvius's texts, indicate that the rotational mechanisms of these cranes were far more advanced than previously recognized. Bearings, designed to reduce friction between moving parts, allowed for smoother rotation, increased load capacity, and remarkably consistent operation. In some cases, these assemblies appear to function on principles strikingly similar to modern ball bearings. The evidence is fragmentary but intriguing. Archaeological sites in Pompeii, Ostia, and Herculaneum have revealed circular tracks, metal rings, and recessed sockets that suggest rotational assemblies capable of distributing weight evenly across a central pivot. When reconstructed, these components reveal a remarkable understanding of load distribution, rotational friction, and material durability. Ancient craftsmen and engineers may have employed bronze or iron balls or similar methods to allow massive crane arms to rotate with minimal effort, long before the industrial age made such assemblies commonplace. Vitruvius provides textual corroboration. In his treatise, De Architectura, he describes lifting devices capable of moving enormous stone blocks, emphasizing the importance of bearings and smooth rotation. While the text does not explicitly describe ball-bearing technology as we know it, the engineering principles are present: careful alignment of axles, reduction of friction, and the need for reliable, repeatable motion. Modern reconstructions show that a circular track lined with lubricated bronze or fitted with smooth pebbles could accomplish what was once assumed impossible for wooden cranes under heavy loads. And yet, the mystery deepens when one examines the tolerances implied by surviving structures. Cranes had to rotate predictably, often with loads that shifted dynamically. A single misalignment could produce catastrophic stress. The metal components that survive, corroded though they are, suggest precision machining, smooth surfaces, concentric grooves, and exact diameters consistent with repeated use. How did Roman engineers achieve such uniformity in an era without standardized industrial tools? How much knowledge of metallurgy, measurement, and alignment was necessary to produce devices that could operate reliably over decades? Some historians suggest that trial, error, and experience explain much of the design. Craftsmen and engineers would have learned by testing progressively larger cranes and refining bearings over generations. Yet the consistency across disparate sites raises the possibility of a formalized body of technical knowledge, a kind of mechanical tradition that included templates, jigs, and practices for achieving near-perfect alignment. If true, this implies a level of organizational and engineering sophistication rarely credited to ancient Rome. Speculative interpretations add further intrigue. Could some cranes have employed early forms of rolling or ball-based bearings, using bronze spheres or hardened wooden rollers to reduce friction? Were some rotational assemblies modular, allowing for repair and replacement without dismantling the entire crane? And if so, why is there so little direct evidence of these innovations? The surviving fragments hint at practices that may have been widespread, yet most wooden components have long since decayed and metal was often recycled, erasing the physical trace of remarkable ingenuity. The implications extend beyond construction. A crane capable of precise, repeatable rotation would have transformed the speed and scale of Roman building projects. Temples, theaters, aqueducts, and harbor structures could be assembled with a degree of control that seems at odds with the limited tools typically attributed to the period. And yet, as with so many ancient machines, the full scope of knowledge is hidden, reconstructed only through careful analysis of surviving fragments, textual references, and the occasional experimental recreation. These cranes, silent in their ruins, speak of an engineering culture that combined practical necessity with subtle mechanical insight. They remind us that precision was not reserved for clocks or astronomical devices. It extended to tools designed to move tons of stone smoothly and safely. In some ways, these ball-bearing rotational assemblies echo the same principles seen in far smaller devices, from the gears of Hellenistic orreries to the triggers of chin crossbows. Attention to friction, alignment, and repeatable motion, scaled up to monumental effect. And yet, questions remain. How widespread was this technology? How many cranes, lifting platforms, or other mechanical systems employed rotational assemblies with precision approximating what we now consider modern engineering standards? Were some components experimental, used only in elite constructions, or lost entirely due to recycling and decay? And most intriguingly, how many other Roman devices, hidden in docks, forts, or temporary construction sites, may have utilized principles of precision engineering that the surviving record barely hints at? As we examine the surviving evidence, run our hands over corroded bronze, and imagine the forces these mechanisms once contained, the scale of ancient ingenuity becomes apparent. These were machines built not only to lift, but to perform with consistent accuracy, marrying brute force with subtle engineering. They invite reflection on the continuity of knowledge, how understanding of mechanics, friction, and motion transcends size and function, appearing in cranes, crossbows, planetary calculators, and beyond. And so, as the cranes of the Roman Empire rotate silently in reconstruction and memory, one cannot help but wonder, what other mechanical marvels, precise, modular, and advanced, were once commonplace, and how much of this ingenuity like the devices we have explored before, has simply been lost to time, leaving only whispers in metal, wood, and stone. As the massive Roman cranes fade from view, their bronze bearings and carefully aligned assemblies quietly tracing centuries of engineering sophistication, our journey shifts from the permanence of stone to the open horizon, from weight to light. From devices built to manipulate matter, we now turn to machines designed to interpret it. Instruments that guided human movement across vast, featureless seas. The Viking Sunstone navigation device emerges from this world, a blend of natural crystal and mechanical insight, a tool of observation as subtle as it was vital. Imagine a cold morning along the jagged coasts of Norway, the fjords shrouded in mist. A longship sits poised, its carved prow reflecting the pale dawn. The crew is preparing to sail, perhaps westward to the British Isles or further to Iceland and Greenland. Visibility is low, clouds hide the sun, yet the journey must continue. Amidst the sailors, one person carries a small, unassuming crystal, translucent, angular, and cool to the touch. This is the Sunstone, a tool whispered about in Norse sagas and medieval texts, a device that could reveal the sun's position even when it is obscured, guiding navigators across hundreds of miles of open water. The concept seems almost magical, a crystal that detects the polarization of sunlight, revealing its angle in the sky. Modern physics confirms that certain minerals, particularly Iceland spar, a form of calcite, can do exactly this. By rotating the crystal and observing changes in light intensity, an experienced navigator could determine the sun's azimuth with surprising accuracy. The technique requires patience, skill, and a subtle understanding of light, yet it offers a lifeline in conditions where compass, stars, or landmarks are unavailable. Historical sources are tantalizing but incomplete. Written accounts from the 13th and 14th centuries mention sunstones used by Viking mariners, though no surviving devices have been definitively identified. Archaeological finds have uncovered crystal fragments in Viking contexts, but their function is often disputed. Were they navigational aids, trade goods, or ornamental objects? Experimental archaeology has demonstrated that crystals can indeed function as polarizers, but the practical skill required to use them effectively suggests a form of knowledge largely oral, passed from master navigator to apprentice. The mystery deepens when considering precision. Determining direction from light polarization demands consistency. The crystal must be held at the correct angle, rotated methodically, and observed under varying atmospheric conditions. Errors in judgment could lead to deviations of tens of kilometers over long voyages. Yet the Norse successfully crossed the North Atlantic, reaching Greenland and Newfoundland centuries before other Europeans. Could the Sunstone, or similar devices, have been the secret behind their remarkable navigational accuracy? Some researchers propose that Viking sunstone techniques were integrated into a broader system of navigation, combining cloud patterns, sea color, wave direction, bird flight, and the sunstone's readings. Others speculate on the possible existence of more complex arrangements, perhaps crystals mounted in wooden frames or rotating mechanisms to aid consistent alignment. While no direct evidence confirms these ideas, the concept aligns with the Vikings' reputation for ingenuity and adaptation, as well as the meticulous observation required for high-latitude sailing. Speculative interpretations extend further. Some suggest that sunstones might have allowed Viking sailors to maintain routes even during polar summers when the sun never sets, or to correct course in storms where visibility was minimal. Could such devices have been standardized within longship fleets? Were they treasured tools, guarded jealously by master navigators, or common instruments distributed among crews? The surviving textual and material record leaves these questions frustratingly open. Scientific experiments add subtle confirmation. Modern tests using Iceland spar demonstrate that sunlight can be located through clouds and fog by observing polarization patterns. Skilled experimenters could achieve directional accuracy within a few degrees, enough to traverse open water reliably. Yet, translating this controlled laboratory observation into daily maritime practice would require both experience and intuition, hinting at the possibility of a largely unrecorded tradition of navigational science among the Norse. The Sunstone also challenges assumptions about ancient technology. It is neither mechanical nor powered by gears. It does not rely on complex machinery or metallurgy. Instead, its sophistication lies in the precise understanding of natural phenomena, light, reflection, and polarization, and the ability to harness them for practical ends. In this sense, it parallels other devices we have explored. The Antikythera mechanism, the chin crossbow triggers, Roman cranes, each relying on careful observation, design, and skill, whether of materials, motion, or energy. And yet, like so many ancient instruments, it resists complete understanding. Without surviving examples or written manuals detailing use, the Sunstone exists largely as hypothesis supported by indirect evidence. Its effectiveness is confirmed in principle, yet its historical prevalence, design variations, and integration into maritime practice remain shrouded in uncertainty. We can reconstruct potential methods, test them experimentally, and infer their utility, but the full scope of Viking navigational sophistication remains elusive. Standing on the deck of a longship, imagining a crystal in hand, the horizon stretching endlessly, one senses both ingenuity and fragility. The Sunstone, simple in form yet profound in application, embodies a form of precision and understanding that parallels the other machines we have explored. Control over movement, motion, or observation with remarkable subtlety. It reminds us that ancient technology was not solely monumental or mechanical. It could be optical, experiential, and deeply practical. And so, as the mist lifts over imagined North Atlantic waters, one cannot help but wonder, how many other tools of subtle precision, small, portable, lost to time, guided human movement, observation, and understanding? How much practical knowledge of light, mechanics, and natural phenomena was preserved orally, transmitted through practice, and then lost to the centuries? The Viking Sunstone stands as a silent testament, urging us to consider that the boundaries of ancient innovation may have been far broader than surviving artifacts alone reveal. As the Viking Sunstone fades from view, its subtle dance with light and horizon lingering in our minds, our exploration moves from navigation across oceans to the careful measurement of time itself. From guiding human motion on open waters, we now turn to guiding motion in machines, devices designed to measure, regulate, and orchestrate with astonishing precision. In this world, the work of Al-Jazari emerges, a brilliant polymath of the 12th and early 13th centuries, whose water clocks and regulating mechanisms hint at a mastery of engineering that seems almost prophetic. Imagine stepping into a dimly lit workshop in Diyarbakir, in what is now southeastern Turkey, around the year 1206 AD. Wooden scaffolds and bronze components fill the space, water trickling softly into carefully carved reservoirs. Gears, pulleys, and levers glint in the faint light, arranged not for decoration but for exact purpose. In the center stands a water clock, a towering, ornate structure, its bronze vessels and floats designed to measure time with unerring regularity. On its surface, mechanical figures rotate, doors open and close, and signals mark the passage of hours. It is both a work of art and an instrument of astonishing precision. Al-Jazari's water clocks were not mere displays of wealth or craftsmanship. They were highly regulated devices designed to maintain consistent timing, even as the volume of water changed or environmental conditions fluctuated. His innovations included float regulators, drips carefully metered by siphons, and escapements that controlled the flow of energy in a way strikingly similar to later European clockwork mechanisms. Each component had to be meticulously shaped, fitted, and aligned. The tolerances were narrow and the surfaces smooth, ensuring that friction, wear, and variation did not compromise accuracy. Historical manuscripts, most notably Al-Jazari's Book of Knowledge of Ingenious Mechanical Devices, describe multiple designs in detail: water clocks with rolling balls that triggered automata, systems that compensated for varying flow rates, and complex gear arrangements that divided time into equal increments. Some water clocks included mechanisms that adjusted for seasonal variation, a testament to the understanding of both fluid dynamics and astronomy. The text itself reads like a combination of engineer's manual and artistic treatise, rich with diagrams, calculations, and practical instructions, yet leaving room for interpretation regarding the precise implementation. Modern reconstructions highlight just how advanced these systems were. Float regulators, for instance, maintained consistent water levels and pressures, ensuring that the release of energy to gears and levers was uniform. Siphons and nozzles were designed to meter small volumes of water with extraordinary control. Bronze fittings were polished to reduce friction and allow the gentle motion of weights and balls. The result was a mechanical orchestra, motion precisely timed, coordinated, and repeated, often for hours or even days. The precision of Al-Jazari's mechanisms suggests a level of standardization and quality control that seems remarkable for the time. How were gears cut to such accurate ratios? How were tolerances maintained across different devices, ensuring consistent performance? Some scholars argue that a combination of skilled labor, carefully developed templates, and incremental refinement over years may explain the result. Yet the uniformity across surviving descriptions, combined with the ability to reproduce complex motions reliably, implies something deeper, an engineering methodology honed and transmitted, perhaps now lost to history. The use of water as both power source and timing medium is particularly fascinating. Water is fluid, unpredictable, and sensitive to temperature, impurities, and pressure. Yet Al-Jazari's designs compensated for these variables with clever mechanisms: float regulators that adjusted for changing volumes, overflow systems that stabilized reservoirs, and escapements that translated irregular fluid motion into consistent mechanical movement. It is a profound example of translating the chaotic into the controllable, a principle we have seen echoed in gear calculators, crossbow triggers, and rotational assemblies across history. Speculative interpretations suggest even more subtle sophistication. Some reconstructions hint at quasi-automated regulation of timing, where mechanisms could self-correct minor deviations in flow or load. Others point to the symbolic integration of movement. Automata and figurines were not merely decorative, but served as indicators of the passage of time, synchronized with precision mechanisms. Could these devices represent a bridge between functional engineering and early computational thought? A system designed to measure, control, and display variables in real time? Yet, as with so many ancient machines, the full scope remains elusive. While Al-Jazari's manuscripts survive, the physical devices are mostly gone, lost to decay, warfare, or the recycling of materials. Wooden components, bronze fittings, and stone supports, all critical to operation, have perished. What remains are texts, diagrams, and the occasional fragment. And from these, we must reconstruct not only motion, but intention, precision, and methodology. How much of Al-Jazari's work was experimental? How many designs were refined over decades? And how many principles were lost alongside the original machines? The challenge is compounded by scale and complexity. Some clocks were small and portable, while others were massive structures, integrating multiple reservoirs, floats, automata, and gear trains. Maintaining precision across such varying scales required a deep understanding of mechanical advantage, fluid dynamics, and material behavior. It suggests a workshop culture where meticulous observation, iterative refinement, and hands-on craftsmanship were essential. And yet, the written record hints at an even broader knowledge: synchronization of multiple devices, seasonal adjustment, and potentially modular components that could be interchanged or calibrated. The legacy of these water clocks extends beyond timekeeping. They represent an early understanding of feedback, regulation, and repeatable motion, concepts central to modern engineering and automation. They demonstrate that precision is not limited to metal gears or astronomical calculations. It can emerge wherever careful observation and thoughtful design meet natural materials, whether water, wood, or stone. They remind us that the manipulation of energy and the measurement of time are deeply connected, and that the line between practical function and artistic expression can be remarkably thin. And yet, questions remain. How many of Al-Jazari's innovations were unique to his workshop, and how many were part of a broader technological tradition now lost? Were these water clocks primarily functional, symbolic, or educational? Did their principles influence later mechanical inventions, transmitted through manuscripts, travelers, or oral instruction? How many subtle details of design, methods for polishing components, measuring flow, or aligning gears have disappeared entirely, leaving only the hints encoded in text and imagination? Standing in the mind's eye before these intricate water clocks, watching floating spheres, cascading streams, and automata triggered with precision, one senses both ingenuity and mystery. Al-Jazari's creations are not only evidence of technical mastery, but also a reflection of a worldview where motion, measurement, and control were interwoven with aesthetics, philosophy, and science. They challenge modern assumptions about what was possible in the 12th century and invite us to consider the full depth of human ingenuity. And so, as we trace the paths of water through copper channels, the rotations of gears, and the movements of figures across platforms, a single question lingers, quiet yet persistent. How much more knowledge of regulation, feedback, and mechanical precision has been lost to time, and what other devices, hidden or vanished, might reveal an even deeper mastery of motion? Machines built not only to perform, but to measure, control, and harmonize with astonishing subtlety. As Al-Jazari's water clocks fade into memory, their streams of water regulating time with near-mechanical perfection, their automata moving in synchrony with unseen gears and floats, our journey turns once more to the land of enduring stone, Egypt. From the subtle precision of fluids and levers, we now return to the tactile, to the slow, deliberate shaping of matter itself. Here, in the workshops of the Nile Valley, we encounter an extraordinary, often overlooked marvel: the Egyptian stone lathe, a turning apparatus that demonstrates a sophistication in machining both remarkable and mysterious. Picture the scene: a quiet workshop illuminated by shafts of sunlight streaming through a narrow doorway. Dust particles float in the warm air, suspended above a long, low bench. On it rests a roughly cylindrical block of granite or diorite, its surface pitted and unpolished, yet poised to undergo a transformation. Nearby, wooden and bronze tools lie within reach: chisels, drills, and cutting implements that, in the hands of a skilled craftsman, will engage in a subtle dialogue with stone. And at the center of this scene is the lathe itself, a device designed to rotate the workpiece smoothly, allowing it to be shaped, hollowed, and polished with an evenness that seems almost inconceivable given its date. The Egyptian lathe is often reconstructed in modern experiments as a manually operated contraption, a spindle supported by two bearings, rotated by cord or bow, with the workpiece mounted between points that allow axial rotation. On the surface, it is deceptively simple. Yet the results defy expectations. Cylindrical stone vessels, bowls, and rods reveal symmetry so exact that modern machine tools struggle to replicate the same uniformity without considerable effort. Walls are evenly thick, surfaces are concentric, and curves are smooth to the touch. For a civilization working thousands of years before the advent of steel lathes or industrial measurement standards, this is remarkable. The archaeological record provides tantalizing clues. Granite vessels from the Old Kingdom, dating as early as 2600 BC, show a consistency in diameter and thickness that implies controlled rotation. Circular grooves and wear patterns on both artifacts and tool fragments suggest not only that rotation occurred, but that it was regulated with careful attention to speed and alignment. Experimental archaeologists have noted that maintaining such concentricity with manual power is extraordinarily difficult. Even small variations in tension or movement could produce irregular surfaces. Yet these artifacts reveal a level of uniformity suggesting knowledge beyond trial and error. Mainstream explanations often emphasize patience, skill, and repetitive motion. Craftsmen would have slowly rotated the stone, abrading it with harder minerals or sand, gradually hollowing and smoothing surfaces over months or years. Yet the precision achieved in some examples raises a provocative question. Was simple abrasion sufficient to produce the symmetry observed? Or did the Egyptians employ a more systematic, controlled method, perhaps an early form of regulated turning? Some experimental reconstructions have posited that cord and bow mechanisms could have acted as rudimentary governors, maintaining relatively consistent rotational speed and reducing human variability. Beyond the mechanics, the tools themselves hint at deeper understanding. Bronze chisels and drills, shaped for specific diameters, indicate that artisans could calibrate cutting depth and angle, producing uniform cavities and external surfaces. Some vessels display perfectly concentric interiors and exteriors, implying careful measurement, template use, or the replication of a rotational standard. Could these workshops have developed techniques for quality control, ensuring that each vessel met precise specifications? And if so, how sophisticated were these methods, and how widely were they shared across Egypt? Speculative interpretations deepen the mystery. The lathe itself could be more than a simple turning device. Could certain setups have allowed for incremental adjustment, correcting alignment as rotation progressed? Were some lathes fitted with crude bearing systems, reducing friction and wear to maintain rotational consistency over long sessions? Did artisans employ water or sand as lubricants to stabilize motion, effectively creating a controlled machining environment centuries before modern technology? The surviving evidence is tantalizingly fragmentary, leaving ample room for conjecture. But the repeated achievement of near-perfect symmetry cannot be dismissed as mere coincidence. The implications are remarkable when considered alongside other precision devices we have explored. Just as Al-Jazari harnessed water to regulate motion, the Romans refined rotational assemblies to manipulate massive loads, and Viking navigators leveraged the subtle physics of light. The Egyptian lathe demonstrates an early grasp of controlled motion and reproducibility. It is a testament to an enduring human drive, the desire to shape matter with predictability, to impose order upon the natural world through careful, repeated action. Yet questions remain. How many techniques, jigs, templates, or rotational guides have been lost to time? How widely were these methods disseminated among workshops or preserved within select artisan families? Did these lathes influence later mechanical thought, or were they an isolated innovation, known only to a few and eventually forgotten as materials, methods, or political circumstances changed? Standing before a vessel turned on such a lathe, smooth, symmetrical, and cool to the touch, one is struck by both awe and humility. It represents not only technical skill, but an understanding of mechanics, control, and precision, that resonates across millennia. The craft reveals a world where human observation, hand-eye coordination, and ingenuity converged to achieve results that challenge modern assumptions about ancient capability. And so, as the stone rotates in the mind's eye, gradually yielding to the tool, polished to perfection, one cannot help but wonder, what other mechanisms, guiding motion with subtle precision, have vanished entirely? How many more machines, simple in form yet extraordinary in effect, remain hidden in the archaeological record or entirely lost, leaving us to reconstruct their principles only through observation, experimentation, and imagination? The Egyptian stone lathe, like every device we have explored on this journey, invites reflection on the limits of what was known and on the extraordinary ingenuity that human hands have achieved throughout history. As the echoes of rotating stone on the Egyptian lathe fade and the deliberate, rhythmic shaping of hard matter lingers in memory, our journey once again turns to light itself, a subtle, almost intangible medium, yet one that ancient humans learned to manipulate with extraordinary skill. From shaping vessels and mechanisms with precision, we now move to shaping perception, to devices that focus, magnify, and reveal what the naked eye cannot see. In the ruins of ancient Nimrud, an optical crystal lens system emerges, a small artifact, yet one that hints at understanding of optics that is both mysterious and profound. Imagine a workshop within the sprawling Assyrian citadel around the 9th century BC. Stone walls are decorated with carved reliefs, sunlight filtering through narrow openings. On a low workbench lies a piece of rock crystal, carefully shaped into a convex lens. It is unassuming in size, perhaps the diameter of a coin, but its polished surface gleams, refracting light with startling clarity. The lens is mounted in a simple frame or perhaps held by hand, yet it performs a function that seems almost inconceivable for the time. It magnifies, concentrates, and focuses, allowing the viewer to perceive detail otherwise invisible. The Nimrud lenses, discovered in the early 20th century amid the ruins of the Assyrian city, have sparked fascination precisely because they challenge our assumptions about ancient technology. Unlike decorative crystal or jewelry, these lenses show signs of deliberate shaping and polishing, designed to produce optical effects. Some have suggested they could magnify inscriptions, aid in engraving, or even concentrate sunlight to ignite tinder or fire. A hypothesis supported by experiments demonstrating that carefully shaped rock crystal can produce a focused beam of light. Yet the true purpose remains unclear. Were these lenses practical tools for artisans, scholars, or astronomers? Or were they symbolic objects associated with ritual, divination, or status? The surviving examples are few and documentation sparse, leaving room for speculation. Unlike the mechanical precision of Egyptian lathes or Al-Jazari's water clocks, these optical devices operate in the intangible realm of light and perception, relying on curvature, surface polish, and material purity rather than gears or levers. The degree of refinement required to produce an effective lens is subtle. Uneven surfaces, inclusions, or slight asymmetry can dramatically degrade performance. That the Nimrud examples appear well-shaped suggests deliberate, controlled craftsmanship. Mainstream explanations propose that these lenses were primarily utilitarian, tools for magnifying inscriptions, examining small objects, or inspecting fine workmanship. Experimental reconstructions show that even a small convex lens can enlarge details by 2 or 3 times, sufficient to assist in engraving, jewelry making, or stone carving. Yet if practical use was the sole purpose, why are so few lenses found, and why are they often associated with elite contexts rather than workshops? Could these lenses also have served as aids to observation of the heavens, early proto-telescopic devices intended to study the stars? Some scholars propose even more speculative possibilities. The precise curvature and transparency of the lenses imply an intuitive understanding of refraction, focal length, and concentration of light, concepts that would not be formally described for millennia. Could these lenses have been used to start fires, focusing sunlight onto small points with enough intensity to ignite material? Could they have been integrated into more complex optical systems, perhaps as magnifying or focusing elements in combination with mirrors or other crystals? There is no direct evidence, yet the potential is tantalizing. The Nimrud lenses also raise questions about technological transmission. How was knowledge of optical shaping preserved, transmitted, or refined? Were lens makers a specialized caste of artisans, practicing a form of knowledge that was part empirical, part experimental, passed down orally or through demonstration? And if so, what other devices or applications might have existed that have vanished without record? The surviving lenses are fragments of a broader story, echoing the lost Hellenistic astronomical calculators, chin crossbows, and Egyptian lathes, evidence of a sophisticated yet partially hidden technological landscape. The craftsmanship is striking in its subtlety. Polishing rock crystal to a convex surface requires patience and a careful sequence of abrasives. Each imperfection could compromise optical function, yet the surviving lenses show remarkable uniformity. Some appear to approach a level of precision sufficient to focus parallel light rays, a property essential for magnification or concentration. The question arises, was this precision intentional, and if so, how was it achieved without standardized measurement tools or modern abrasives? Did the Assyrians employ rotational lathes for stone, rudimentary templates, or other methods now lost to time? Experimental archaeology suggests that the lenses could have served multiple functions simultaneously: magnifying, focusing, and even symbolic representation. In contexts where power, knowledge, and technology intersected, a lens might have represented insight, control, or the ability to see beyond ordinary perception. Were these objects used by scholars to study small inscriptions, by artisans to refine detail in carved objects, or by priests to harness the mysterious properties of light? The ambiguity itself is part of their allure. Moreover, the Nimrud lens reminds us that technological sophistication is not always monumental. Unlike cranes, crossbows, or planetary gear systems, the precision required here operates at a micro-scale, in the invisible manipulation of photons rather than the visible movement of matter. Yet, the underlying principles, observation, measurement, control, and repetition, mirror the same logic that guided Al-Jazari, the Egyptians, and Roman engineers. Precision can exist in any medium, whether water, stone, bronze, or light. And yet, despite experimentation and reconstruction, the full story remains elusive. How many optical devices existed in the ancient Near East, and what purposes did they serve? Were lenses part of a larger toolkit for artisans, astronomers, or scholars? Or were they rare curiosities, valued for their rarity and symbolic power? How much knowledge of light, refraction, and focus has been lost, leaving only these tantalizing fragments to hint at broader mastery? Standing before a Nimrud lens, imagining sunlight or torchlight passing through its polished curvature, one senses both human ingenuity and mystery. A small, unassuming piece of crystal becomes a window into ancient perception, a testament to experimentation, observation, and control over phenomena we often take for granted. It bridges the tangible and intangible, the practical and the speculative, inviting us to reconsider the boundaries of technological understanding in the ancient world. And so, as we trace rays of light through the lens in imagination, as we consider the artisans who may have shaped it, the scholars who may have studied through it, and the unknown applications that remain hidden, one question persists. How many other optical, microscale, or otherwise subtle devices existed across ancient civilizations, designed with precision, observation, and intention? And what other secrets of light, motion, and control are still waiting, unseen, beneath the layers of history? As the Nimrud optical lens fades from view, its delicate manipulation of light hinting at a profound understanding of perception and focus, our journey moves now from observation of the natural world to the measurement of time itself, not in water, stone, or celestial spheres, but through the cycles of days, months, and years. Across oceans and continents, in the dense jungles of Mesoamerica, the Maya developed machines and assemblies that calculated, tracked, and predicted temporal patterns with astonishing accuracy. Here, among the stone temples and pyramids of the Yucatan, we glimpse the legacy of rotational calendar computation assemblies, mechanical or semi-mechanical devices designed to bring order to cosmic cycles. Imagine standing in a shaded chamber within a Maya temple, the air heavy with the scent of earth and resin. Sunlight filters through carved stone openings, illuminating the edges of glyph-covered slabs and cylindrical objects arranged with care. Some of these artifacts, interpreted by scholars as parts of calendrical devices, show grooves, rotating discs, and interlocking rings, suggesting a system that could turn, align, and indicate the passage of time. Unlike static carvings, these assemblies appear designed for movement, for cyclical rotation, tracing the intricate interplay between solar years, lunar months, and planetary observations. The Maya calendar system itself is extraordinary in its complexity. The Tzolk'in, a 260-day ritual calendar, the Hob, a 365-day solar cycle, and the Long Count, a continuous count of days over millennia, were synchronized with precision. Yet the question arises, how did the Maya manage such calculations, often without the aid of paper, ink, or surviving gear-based mechanisms? Archaeological and iconographic evidence suggests that rotational devices, possibly wooden or stone discs with pegs, markers, and notches, could have functioned as computational tools, allowing priests, astronomers, and scholars to align cycles, predict eclipses, and maintain continuity over generations. The surviving artifacts hint at both mathematical sophistication and mechanical ingenuity. Some cylindrical stones feature grooves and incisions suggesting rotational alignment with celestial observations. Certain monuments depict hands turning discs or spheres, perhaps indicative of interactive tools used to calculate calendrical cycles. The repetitive nature of these grooves and markers implies that motion was central. These were not static diagrams, but dynamic systems where rotation translated into computation. By aligning disks with visible celestial bodies, or by advancing them according to mathematical rules, the Maya could anticipate important dates and celestial events with precision that rivals later European astronomical tables. Mainstream interpretations emphasize the brilliance of Maya arithmetic, including their use of zero, positional notation, and long-term counting systems. Yet the combination of abstract computation and tangible rotation suggests a hybrid approach, part mechanical, part observational, part mnemonic. Could the physical act of turning disks, aligning pegs, and watching rotational markers have reinforced calculations, making complex cycles tangible and manipulable? The possibility evokes parallels with Hellenistic gear mechanisms, Al-Jazari's water clocks, or even Roman rotational assemblies. Different materials, different cultures, yet a shared human impulse to transform abstract time into controlled, observable motion. Speculative reconstructions go further. Some suggest that multiple rotating disks may have been linked, producing composite cycles where the rotation of one disk governed the movement of another, an early, indirect form of mechanical computation. Could this have enabled the prediction of solar eclipses, planetary conjunctions, or ceremonial dates decades in advance? Were some assemblies large and stationary, incorporated into temple architecture, while others were smaller, portable, and used in field observation? The surviving evidence is tantalizing but inconclusive, leaving much to imagination tempered by the rigor of archaeology. The precision implied is remarkable. Even slight misalignment in markers or rotational increments could compound over months and years, producing significant errors in predicted cycles. Yet the Maya calendars, corroborated by inscriptions and historical records, indicate a mastery of synchronization that required both mathematical insight and meticulous application. Could the physical rotation of these assemblies, combined with careful observation, have provided a form of error correction, a mechanical analog to modern feedback systems? It is a possibility hinted at by the interlocking nature of some surviving discs and the consistent repetition of numerical patterns in their carvings. Cultural context also deepens the mystery. Time in Maya society was not merely a measurement, it was a lens through which the cosmos, divinity, and human action were understood. Precision was both practical and symbolic, aligning rituals, agricultural cycles, and political events with celestial regularity reinforced cosmic order. Could these rotational computation assemblies have served not only as practical calculators, but as instruments for aligning human behavior with perceived universal harmony? If so, their function transcends mathematics or mechanics, entering a domain where precision, ritual, and cosmology converge. And yet, as with so many ancient machines we have explored, questions remain unanswered. How widespread were these rotational assemblies? Were they standardized or unique to particular temples or priestly lineages? What materials, wood, stone, or metal, were used? And how were the mechanisms maintained over generations? How many of these devices have vanished entirely, leaving only glyphs, iconography, or indirect evidence to hint at their existence? Standing before a reconstructed disk or envisioning the alignment of rotating markers in a temple chamber, one senses the same awe that accompanies a finely polished lens, a lathe-shaped vessel, or a meticulously balanced water clock. The Maya, like other civilizations we have explored, translated observation, calculation, and mechanical intuition into tangible devices. They transformed the abstract cycles of days and years into rotating, manipulable systems, bridging human cognition and cosmic rhythm with subtlety and ingenuity. And so, as we trace the turning of disks in imagination, aligning markers with sun, moon, and stars, one question lingers. How many other devices, lost to time or buried in the dense jungle, carried the same blend of precision, motion, and cosmic insight? How many mechanisms allowed the Maya to manipulate time itself, rotational assemblies that computed, synchronized, and predicted, with accuracy that continues to astonish modern observers? The answer remains hidden, waiting for discovery, reconstruction, or interpretation, reminding us once again that the pursuit of precision is a universal thread in human ingenuity. As the Maya rotational calendar assemblies fade from view, disks turning silently in temples, aligning ritual, celestial, and agricultural cycles with uncanny precision, our journey shifts from the manipulation of time to the control of force itself, and from distant jungles to the sun-baked landscapes of the Aegean. On the island of Crete, the Minoan civilization flourished millennia ago, constructing palaces and fortifications whose scale and complexity continue to inspire awe. Amid these architectural marvels, one subtle feature often escapes notice: stone interfaces engineered to survive the relentless tremors of the Earth. Early examples of seismic-damped mechanisms that reveal a sophisticated understanding of material, weight, and motion. Picture the labyrinthine palace of Knossos, its walls rising in tiers, frescoes glowing with color, and corridors winding between massive columns and terraces. Though the palace appears static, immovable, it was built in a region of frequent earthquakes, where the ground itself shifted unpredictably. Yet the structures endured, often with surprisingly little damage, despite centuries of tremors. Close examination of the masonry reveals something remarkable. Carefully cut stones resting upon one another with subtle interlocking shapes, polished surfaces, and occasionally layered with materials that absorb or redirect energy. These are not mere walls. They are carefully designed mechanical interfaces, translating destructive kinetic energy into controlled, damped motion. Archaeologists have noted that columns, lintels, and floor slabs often sit upon plinths or bases shaped to allow slight rotation or rocking under stress. Certain blocks are rounded or beveled at their contact points, reducing friction and permitting minute adjustments as the building moves. In some cases, thin layers of clay or organic material appear to have been inserted between stones, functioning as primitive shock absorbers. Together, these elements suggest an intentional approach, not simply piling stone atop stone, but creating a system in which seismic energy could be dissipated without catastrophic failure. Mainstream explanations attribute this durability to skilled craftsmanship, material selection, and empirical observation accumulated over generations. Minoan builders may have recognized patterns, that certain shapes, arrangements, and materials survived tremors better than others. They may have developed rules of thumb passed down through apprenticeship, allowing massive palaces to withstand forces that would have reduced other structures to rubble. Yet the precision and consistency of these interfaces provoke further reflection. Were these features merely practical, or did they involve a deeper understanding of force distribution, damping, and dynamic response, principles that would not be formally articulated for millennia? Experimental archaeology provides compelling insight. Reconstructions of Minoan walls and columns subjected to simulated seismic activity reveal that subtle curvatures, interlocking joints, and damped interfaces significantly reduce stress concentration. Rounded bases allow stone blocks to roll minutely, dispersing energy across a broader surface, while friction-modulating layers slow movement, preventing sudden collapse. Even minor differences in the placement or polish of a contact surface can change a wall's performance dramatically. The results suggest not random adaptation but controlled, deliberate design, ancient engineering at a level rarely appreciated. Speculative interpretations extend the mystery further. Some researchers propose that Minoan builders may have developed standardized modular interfaces, allowing damaged stones to be replaced or realigned without dismantling entire walls. Others suggest that certain features, such as rounded plinths or beveled grooves, could have been optimized through careful experimentation, producing repeatable responses to tremors, a proto-engineering methodology for structural resilience. Could it be that Minoan architects understood not only how to build, but how to engineer controlled motion within seemingly rigid stone? The implications are profound. Unlike gears or water clocks, these devices are passive. They harness natural forces rather than drive mechanical motion. Yet the sophistication is unmistakable. Each stone interface represents a delicate balance of weight, friction, and elasticity, a small machine embedded within massive construction. It demonstrates a mindset attuned to observation, experimentation, and subtle control, principles that echo across the civilizations we have explored, from Al-Jazari's water regulators to Roman ball-bearing assemblies and Egyptian lathes. Precision is not always about rotation or measurement. It can also manifest in the management of natural forces over large scales. The cultural and practical context further enriches the mystery. Earthquakes were a constant threat, yet Minoan palaces remained centers of administration, ritual, and daily life for centuries. Precision in stone interface design was not merely technical. It was necessary for survival, continuity, and the functioning of society. The same structures that housed frescoes, ceremonial halls, and storage rooms also embodied knowledge of material behavior, dynamic stability, and energy dissipation. It is a reminder that technological sophistication can be hidden within what appears to be ordinary architecture, blending artistry with engineering, ritual with mechanics. Yet, as with many ancient devices, questions remain unanswered. How systematic was this knowledge? Were there treatises, guidelines, or oral traditions detailing the design of damped stone interfaces, or was it entirely empirical? How much trial, error, and observation contributed to their refinement? And how widely were these techniques disseminated? Were they unique to Crete, or part of a broader Aegean engineering tradition now mostly lost to time? The surviving evidence is tantalizingly partial, preserved only in the alignment of stones, traces of inserted materials, and the remarkable survival of structures through centuries of seismic events. Standing within a partially reconstructed palace, one can almost feel the subtle response of the building under imagined tremors. Stones shifting imperceptibly, columns rocking fractionally, energy absorbed and dissipated before it reaches destructive peaks. It is a dynamic mechanical system hidden in plain sight, a silent testament to observation, precision, and adaptation. The Minoan Seismic-Damped interfaces embody the same human impulse that drives other machines we have studied, to measure, control, and manipulate forces with care, foresight, and skill. And so, as we trace the hidden pathways of energy through the joints, plinths, and bases of these ancient walls, one question remains. How many other devices, subtle and overlooked, allowed civilizations to bend natural forces to their will? How many examples of atomic-level precision, embedded in stone rather than metal, waiting to be interpreted, remain lost beneath centuries of rubble, vegetation, and time? The Minoan seismic-damped stone interfaces remind us that ingenuity is not always monumental or immediately visible. It can be concealed within the interface of matter and motion, quietly performing work that withstands both the ages and the tremors of the earth itself. As the Minoan seismic-damped stone interfaces recede from our imagination, massive columns and walls subtly moving, absorbing the hidden forces of the earth, we shift our attention from the ancient mastery of static materials to the dynamic manipulation of fluids. In the arid landscapes of the Levant, carved into cliffs and plateaus, the Nabataeans built cities of stone and ingenuity. Petra, with its rose-colored facades and labyrinthine water channels, conceals a level of hydraulic engineering that continues to astonish scholars. Pressure-balanced valves capable of controlling water flow with remarkable subtlety, precision, and foresight. Imagine walking through a shaded canyon in southern Palestine, sunlight striking sandstone cliffs that glow red and gold. The air is dry, and the sound of flowing water is rare and precious. Within the rock-cut channels and cisterns, water moves silently, guided by conduits, tunnels, and chambers. And somewhere within these hidden arteries, a mechanism lies, a carefully shaped stone or bronze valve designed to regulate pressure, maintain flow, and prevent surges that could damage the city's intricate hydraulic network. These are not crude stopcocks. They are precision instruments reflecting an intimate understanding of fluid dynamics long before formal theory existed. The Nabataeans relied on a delicate balance. Rainfall was sporadic, yet their cities demanded a continuous supply of water for drinking, irrigation, and ritual. To achieve this, they engineered cisterns connected by channels of varying diameter and gradient, often spanning kilometers. Within these networks, pressure imbalances could threaten stability. Sudden inflows could flood channels or damage infrastructure, while inadequate flow could leave parts of the city dry. The solution appears to have been hydraulic valves designed to balance these forces, mechanisms that could open or close in response to pressure, maintaining equilibrium across the system. Archaeological surveys of Petra and surrounding sites have revealed channels, cisterns, and carved stone fittings suggestive of these valves. Some exhibit concave cavities, tapered openings, or pivot points consistent with movable plates or plugs shaped to respond to variations in water pressure. Experimental reconstructions indicate that such designs could automatically regulate flow. As pressure increased in the upstream channel, a floating element or weighted plug would rise, partially closing the passage and reducing flow. As pressure fell, the element would lower, allowing water to pass freely. The result is a passive, self-regulating system, mechanical intelligence embedded in stone, anticipating the variability of nature without human intervention. Mainstream explanations emphasize empirical trial and observation. The Nabataeans, living in a harsh desert environment, may have discovered through experience that certain shapes, materials, and positions maintained flow more reliably than others. Repeated use and careful observation could refine these mechanisms over decades, producing consistent, reliable behavior. Yet the precision apparent in some sites suggests more than mere experimentation. The curvature of chambers, the balancing of floats, and the integration of multiple valves into a network imply systematic design principles, an engineering methodology that marries observation with predictive calculation. Speculative reconstructions deepen the intrigue. Could some valves have been designed to respond not only to pressure, but also to flow rate, temperature, or even sediment load? Were there variations in design for irrigation versus urban supply, or for cisterns connected to aqueducts versus those fed by springs? Some researchers suggest that certain carved stone shapes could have functioned as early forms of feedback, automatically distributing water between multiple channels according to demand, a primitive hydraulic analog of regulation and control that would prefigure modern fluid mechanics. The ingenuity is further revealed when considering the materials and construction. Channels often incorporate smooth sandstone, carefully polished to reduce friction and prevent erosion, while valves are shaped to fit precisely, minimizing leakage and ensuring responsiveness. Some systems integrate stepped chambers or small dams, controlling flow velocity and pressure gradients over long distances. The Nabataeans, lacking formal mathematical models, relied on observation, incremental refinement, and meticulous craftsmanship to achieve effects that modern engineers would recognize as sophisticated hydraulic control. The context is equally compelling. Water was life in the desert. Mismanagement could devastate crops, deplete cisterns, or undermine a city's stability. Precision in hydraulic regulation was thus both practical and vital. The same systems that quenched the thirst of inhabitants also enabled ceremonial cleansing, supported architectural grandeur, and ensured the functioning of a complex urban environment. These valves were not mere conveniences. They were instruments of survival and prosperity, embedding subtle mechanical intelligence into the stone arteries of a desert civilization. Yet, like many ancient machines, mysteries remain. How widespread were pressure-balanced valves across Nabataean cities? Were their designs transmitted orally through apprenticeship or encoded in standardized templates? How many variations existed, each optimized for specific conditions or flow rates? And crucially, how much of this knowledge has been lost with the decline of the Nabataean civilization and the gradual abandonment of Petra and other sites? The surviving artifacts are fragments, tantalizing glimpses into a broader technological landscape that may once have been far more elaborate. The precision of these mechanisms also resonates with other devices we have explored, like Minoan seismic-damped stones, Egyptian lathes, and Al-Jazari water regulators. Nabataean valves demonstrate an understanding of forces and motion, albeit in fluid, rather than solid or mechanical form. The principle is consistent. Observation, refinement, and subtle control produce outcomes that seem impossibly precise for the era. Nature, unpredictable and powerful, is harnessed through design, observation, and craftsmanship, whether in stone, water, or crystal. Standing in imagination before a carved valve, observing how a weighted plug might rise and fall with the pressure of flowing water, one senses both simplicity and sophistication. The mechanism is silent, passive, yet responsive, a machine designed to think, in a sense, about the variability of its environment. It embodies the same drive we have witnessed across civilizations, the desire to measure, control, and harmonize natural forces with human intention. And so, as we trace water through the carved channels of Petra, envisioning cisterns, conduits, and valves responding to seasonal floods or daily consumption, one question persists. How many other hydraulic mechanisms, pressure-sensitive, self-regulating or otherwise, have been lost to time, leaving only fragments in stone to hint at their existence? How many more subtle machines, balancing forces with precision, await discovery beneath the desert sands, silently testifying to human ingenuity and the enduring pursuit of control over nature itself? As the Nabataean hydraulic valves fade from memory, their quiet, responsive regulation of water through stone channels and cisterns, balancing pressure with subtle intelligence, we now turn to a civilization whose mastery of motion was expressed through the marriage of water and machinery. In the rolling hills and bustling settlements of ancient Rome, engineers transformed flowing streams into labor-saving devices, creating systems that harnessed rotational energy with remarkable ingenuity. Among these marvels were water-powered differential milling mechanisms, complex machines that hint at a sophisticated understanding of motion, force distribution, and mechanical computation, long before the advent of modern gearing. Picture a mill situated beside a Roman aqueduct, the steady roar of water striking a vertical wheel, turning it with rhythmic precision. Dust and grain swirl in the air, mingling with the scent of wood and freshly milled flour. Beyond the surface simplicity, within the carefully aligned shafts and cogged wheels, a hidden mechanism adjusts rotational speed, distributes torque, and balances the movement of multiple millstones. This is not merely a water wheel. It is a system in which motion is directed, measured, and modulated, an early example of differential technology translated into tangible labor. Archaeological and literary sources suggest that Roman engineers developed differential gears to drive milling machinery, allowing two millstones to rotate at different speeds while maintaining overall coordination. Such mechanisms would have allowed for the simultaneous processing of different grains, adjustment for consistency, and even mitigation of stress on structural components. The differential concept, commonly associated with modern vehicles, appears in these ancient mills as a practical solution to a mechanical problem: how to manage multiple rotational outputs from a single water source without losing control or efficiency. The surviving evidence is both fragmentary and tantalizing. Excavations of Roman mill sites, such as those along the river Barbegal in southern Gaul, reveal massive masonry channels, water wheels, and remnants of gear assemblies. Some of these gears show precise interlocking teeth cut with uniform spacing and alignment. Wear patterns indicate repeated, controlled rotation, suggesting that these were not haphazard devices but carefully engineered systems. The design implies understanding not only of rotation but also of torque distribution, load balancing, and the translation of linear water force into rotational work. Mainstream explanations emphasize practical problem-solving, engineers responding to the demands of large-scale grain production, using observation, iterative refinement, and empirical knowledge to develop effective mechanisms. Yet the precision of these surviving assemblies raises further questions. The interlocking gears, the alignment of shafts, and the smooth integration of multiple millstones suggest deliberate calculation and standardization. Could Roman engineers have understood principles analogous to modern differential mechanics, applying them in ways that allowed mills to operate continuously, efficiently, and with minimal human intervention? Experimental reconstructions of water-powered mills support this possibility. By arranging multiple gears in differential configurations, researchers have replicated the ability to rotate two stones at variable rates from a single water wheel. The distribution of torque prevents overload, while small adjustments in gear alignment enable fine control over milling speed and grain consistency. Such results imply that Roman engineers, without modern mathematical notation or materials, could achieve functional equivalence of differential regulation, a form of mechanical intelligence embedded in gear ratios and rotational alignment. Speculative interpretations deepen the intrigue. Could some mills have incorporated even more advanced features, such as automatic load adjustment or synchronization of multiple stone pairs across separate water wheels? Were the Romans experimenting with concepts akin to feedback control, using the resistance of the grain and the flow of water to self-regulate milling performance? Some scholars suggest that the design of multi-tiered mills, where water flows sequentially from one wheel to another, represents an early understanding of staged energy distribution, a principle strikingly similar to modern mechanical engineering solutions. The engineering is further enhanced by the materials and construction techniques. Bronze and iron fittings, carefully shaped wooden axles, and stone-bearing surfaces allowed the differential assemblies to operate reliably under continuous load. Water, an unpredictable and fluctuating source of energy, required mechanisms that could absorb sudden surges, adjust rotational speed, and prevent damage to fragile components. The integration of differential gears with water wheels represents a holistic understanding, one that merges material science, fluid dynamics, and mechanical design into a coherent system. The social and practical context is equally compelling. Grain was the lifeblood of Roman cities. Ensuring consistent, high-volume milling was critical for feeding urban populations, maintaining stability, and sustaining economic activity. The precision of differential milling mechanisms was not an abstract pursuit. It had immediate, tangible consequences for survival and prosperity. The same attention to motion, balance, and control evident in these mills echoes patterns we have observed in other civilizations, from Nabataean hydraulic networks to Egyptian lathes and Al-Jazari's water regulators. Human ingenuity applied to harmonize forces, manage energy, and extend capability. Yet, as with so many ancient machines, mysteries remain. How many variations of differential milling mechanisms existed, and how standardized were they across the empire? Were these systems limited to elite, large-scale production sites, or were simpler versions widespread in smaller settlements? How did knowledge of differential gearing propagate among engineers, and to what extent was it codified versus preserved through apprenticeship and practice? Archaeology provides fragments, but the full picture, every gear ratio, every shaft alignment, every nuanced technique, remains largely lost to time. Standing beside a reconstructed water-powered mill, watching the wheels turn, and imagining the subtle rotation of differential gears beneath the stone, one senses the same wonder that accompanies a finely crafted lens, a lathe-polished vessel, or a pressure-balanced valve. The Romans, like other civilizations we have explored, harnessed observation, refinement, and careful design to impose order on dynamic forces. They translated the unpredictable flow of water into consistent, controlled motion, embedding mechanical intelligence in rotation, torque, and interlocking components. And so, as we envision the spinning millstones, the interwoven gears, and the flowing water that drives them, one question lingers. How many other water-powered machines, differential systems, or energy-distributing mechanisms existed across the ancient world, designed with precision that rivals modern engineering, yet vanished entirely, leaving only traces in stone, metal, and imagination? The Roman differential milling mechanisms remind us once again that human ingenuity has always sought to measure, control, and harmonize forces, whether in stone, fluid, or gear, and that many secrets of mechanical mastery still lie hidden, waiting to be rediscovered. As the Roman differential milling mechanisms turn silently in our imagination, gears meshing, water flowing, millstones spinning in precise, coordinated motion, we leave the world of rotational energy harnessed from rivers and aqueducts and turn to a civilization that expressed mastery at the opposite extreme: the minuscule, the meticulous, and the almost invisible. Along the banks of the Indus River nearly 5 millennia ago, the cities of Harappa and Mohenjo-Daro flourished, and within their streets and marketplaces, we find evidence of a quiet yet astonishing technological sophistication. Micro-calibrated measurement weights. Small, unassuming, and often overlooked, these weights embody a level of precision that challenges assumptions about what ancient humans could achieve, and hints at a society deeply attuned to consistency, trade, and measurement. Picture a bustling Indus Valley street, the aroma of baked bread, roasted grains, and river water mingling in the heat of the day. Merchants arrange their goods, beads, metals, grains, and spices, on simple balance scales. In their hands are small cubical weights, carved from stone or molded from bronze, each uniform in size, shape, and mass. Some weigh less than a few grams, others a few tens of grams, yet all conform to remarkably consistent standards, with tiny variations often within a fraction of a gram. For a civilization that left no deciphered writing explaining its mathematical or measurement systems, the consistency of these weights is extraordinary, revealing both empirical skill and a conceptual framework for precision. Archaeological excavations across Indus sites have uncovered sets of these weights, often arranged in multiples of a standard unit. The stones are smoothed and carefully shaped, some with incised markings, others perfectly cubical, reflecting an attention to symmetry and uniformity. Comparative analysis of weights from distant settlements suggests a common standard, indicating that traders, artisans, and administrators across hundreds of kilometers adhered to shared conventions. How did they achieve such consistency without graduated scales or calibrated balances as we understand them today? The precision is so striking that modern replicas often require careful measurement and adjustment to achieve the same tolerances. Mainstream explanations emphasize trade and economic necessity. In a networked civilization spanning urban centers, standard weights would facilitate fair exchange, taxation, and record-keeping. Yet the precision achieved is almost microscopic, far beyond the practical requirements of simple barter. Some weights are calibrated to fractions of a gram, accuracy that anticipates modern mass measurement. Could this suggest a deeper understanding of proportionality, ratios, and standardized units? Did Indus artisans possess methods for refining stone or metal to near-perfect specifications, perhaps using empirical trial and error, repeated measurement, or carefully crafted templates? Experimental reconstructions provide fascinating insight. Using primitive tools such as abrasives, chisels, and balance scales, modern researchers have attempted to reproduce Indus weights. Success requires patience, subtle adjustment, and repeated testing, implying that the original makers likely employed similarly methodical techniques. Certain weights appear designed to nest together, forming sets that allow combinations for precise calculation of mass. Others are perfectly cubical, reducing error from uneven edges. The craftsmanship suggests both practical skill and an appreciation for modular, scalable measurement systems, a conceptual elegance that complements the physical precision. speculative interpretations extend the mystery. Were these weights purely for commerce, or did they also serve scientific, ritual, or administrative purposes? Some scholars suggest that their uniformity and multiplicity could have enabled complex calculations, inventory management, or standardized construction measurements, hinting at a proto-technical understanding of units and proportionality. Others point to the possibility that they played a role in ritual or social regulation, a precise balance between materials, offerings, or commodities, echoing a cultural ethos of harmony, equivalence, and order. The degree of calibration also invites questions about the technology behind it. Some weights show almost identical mass across great distances, implying a system of standardization maintained over generations. How was this achieved? Were there central authorities or guilds that controlled production, testing, and distribution? Did artisans use reference weights repeatedly, adjusting until achieving uniformity, or did they have specialized tools capable of measuring subtle differences, lost to history? The answers remain elusive, yet the surviving artifacts suggest a sophistication that parallels mechanisms we have seen elsewhere, from Roman differentials to Nabataean hydraulic valves, though manifested at a micro scale rather than in flowing water or moving gears. The social implications are equally profound. Consistent measurement would have been essential in a society where trade extended across hundreds of kilometers, involving metals, grains, and other commodities of varying density and value. Precision weights would have enabled trust between merchants, fairness in taxation, and predictability in exchange, a technological solution to social and economic complexity. The concept of atomic-level consistency, whether in mass, distance, or force, appears repeatedly across civilizations. Yet in the Indus Valley, it manifests in objects so small and unassuming that their significance can easily be overlooked. Yet, like so many ancient innovations, questions remain unanswered. How were these standards developed and maintained? How widespread were sets of micro-calibrated weights, and did they represent uniform units across the entire Indus civilization, or vary locally? How were artisans trained to achieve such precision, and what tools or methods supported their work? Could some weights have been experimental, refined over decades, or even centuries, as measurement standards evolved? The surviving artifacts offer tantalizing evidence, but the broader network of knowledge, practice, and distribution remains largely invisible. Standing before a tray of reconstructed Indus weights, one can appreciate both their simplicity and subtle complexity. Each small cube, polished and consistent, embodies observation, repetition, and control, principles that resonate with other ancient machines we have explored. Like a lens focusing light, a differential mill distributing torque, or a hydraulic valve balancing pressure, these weights convert understanding into tangible form, imposing order and predictability onto the world. Micro-scale precision, it seems, was as valued and achievable as macro-scale engineering. And so, as we imagine the hands of Indus merchants, artisans, or administrators delicately placing each weight, balancing scales, and verifying consistency, one question persists. How many other miniature devices, measurement systems, or micro-calibrated instruments were developed across ancient civilizations, achieving a level of precision that challenges modern assumptions? How many secrets of human ingenuity, encoded in small, unassuming objects, still await discovery, reminding us that the pursuit of accuracy, whether in stone, metal, water, or grain, has always been a defining aspect of civilization itself? As the Indus Valley micro-calibrated weights slip from view, tiny cubes of stone and bronze embodying meticulous precision across vast trade networks, we move now to another civilization that mastered a different form of exactness: the casting of metal with astonishing repeatability. Along the banks of the Yellow River, in the heart of Bronze Age China, artisans and metallurgists developed systems for precision casting that transformed molten bronze into tools, ritual objects, and weapons with uncanny consistency. Here, the chaos of fire and molten metal was tamed, controlled, and shaped into exact forms, revealing a technological sophistication that speaks to both practical necessity and profound ingenuity. Imagine entering a workshop at Anyang, the heart of the Shang Dynasty, around 1200 BC. The air is thick with smoke and the scent of heated metal. Embers glow in crucibles, and molten bronze is poured with care into carved molds. Each mold, often complex, multi-part, and intricately carved, transforms fluid metal into objects of precise size, thickness, and ornamentation. The surfaces of ritual vessels, weapons, and tools bear patterns and inscriptions so consistent that the variation between casts is often almost imperceptible, suggesting a calibration and foresight that borders on engineering genius. Archaeological evidence reveals the sophistication of these casting systems. Clay molds were carefully constructed in sections, designed to withstand repeated heating while maintaining dimensional fidelity. Wax or clay cores defined hollow spaces with remarkable consistency, allowing the production of vessels and objects that were both structurally sound and visually symmetrical. Some molds contain intricate interlocking features, guiding the flow of bronze and preventing defects caused by turbulence or uneven cooling. Even minor adjustments in the thickness of mold walls, the angle of sprues, or the design of vents suggest careful attention to thermal expansion and contraction, factors that modern metallurgists still consider critical in precision casting. Mainstream interpretations emphasize practical motivations. Ritual vessels, ceremonial weapons, and standardized tools required consistency for symbolic, functional, or economic reasons. Yet the precision achieved often exceeds what is necessary for mere utility. Certain sets of molds produce near-identical vessels or weapons, allowing interchangeable parts and exact replication across generations. How did Bronze Age metallurgists achieve such uniformity without written technical manuals, advanced measuring devices, or thermometers? The answer may lie in empirical knowledge accumulated over centuries, combined with meticulous control over materials, temperature, and mold design. Experimental reconstructions provide insight into the techniques behind this precision. Researchers pouring bronze into replica molds have noted that slight variations in temperature, alloy composition, or mold alignment produce measurable differences in the finished objects. Maintaining consistency requires both experience and careful observation, suggesting that Shang artisans relied on standardized procedures, iterative refinement, and perhaps even calibrated reference molds to maintain uniformity. Could these systems represent an early form of industrial control where the behavior of molten metal, molds, and cores was understood well enough to predict outcomes reliably? Speculative interpretations expand the intrigue. Some scholars suggest that certain molds, with precisely carved interlocking features and channels, may have been designed to regulate flow and cooling, functioning as passive control systems for the molten metal. Others note that repeated patterns in vessels and weapons indicate a conceptual understanding of symmetry, proportion, and material behavior that approaches modern engineering principles. Did Shang metallurgists develop a form of calibration comparable to that seen in Indus Valley weights or Roman mills, translating empirical observation into repeatable results? The surviving artifacts hint at such possibilities, though much remains conjectural. The technological sophistication is further highlighted by the scale and variety of castings. Bronze vessels range from small ritual cups to massive, elaborately inscribed tripods. Weapons include swords, axes, and spearheads of consistent length, weight, and balance. Each object required careful mold design, precise control of molten metal, and careful cooling to avoid warping or cracks. The degree of repeatability, often imperceptible to the casual observer, suggests a system of knowledge where molds, materials, and process were treated as an integrated mechanism, calibrated to produce predictable outcomes every time. The cultural context underscores the importance of this precision. Bronze objects were not merely functional. They carried social, ritual, and political significance. Vessels inscribed with clan names or ceremonial markings required consistency to uphold symbolic meaning. Weapons needed uniformity to ensure combat effectiveness and fairness among soldiers. Even seemingly mundane tools, produced with careful calibration, reflect a broader societal emphasis on order, reliability, and technical mastery. Precision in casting was a conduit for both power and stability, extending from individual artisans to entire dynasties. Yet, as with many ancient innovations, mysteries remain. How exactly did Bronze Age metallurgists control temperature with such consistency? Were molds standardized across workshops, or was each set bespoke, refined through observation and repetition? How much empirical knowledge, transmitted orally or through apprenticeship, underpinned the remarkable uniformity of these artifacts? Could some designs represent lost principles of flow control, thermal management, or even early experimentation with alloys that allowed predictable expansion and contraction? Archaeology provides tantalizing fragments, but the full scope of their metallurgical knowledge remains hidden. Standing before a meticulously carved mold or examining a cast bronze vessel, one senses both simplicity and extraordinary sophistication. These objects, produced thousands of years ago, embody observation, control, and precision in ways that resonate with other ancient machines we have explored, from Indus micro-calibrated weights to Roman differential mills and Nabataean hydraulic valves. Each reflects the human drive to impose order on a complex and often chaotic world, translating natural forces, whether molten metal, water, or grain, into predictable, reproducible outcomes. And so, as we watch in imagination the molten bronze flowing into interlocking molds, settling and cooling into perfect form, one question persists. How many other systems of precision, hidden in the fire and clay of ancient workshops, remain undiscovered or misunderstood? How many secrets of material control, calibration, and repeatable engineering have been lost to time, leaving only the surviving objects as hints of a sophisticated technological past? The Chinese Bronze Age precision casting mold systems remind us once again that human ingenuity often hides in plain sight, embedded in form, process, and subtle control, waiting to be appreciated and understood. As the Chinese Bronze Age precision casting molds cool in our imagination, the molten metal hardened into objects of flawless symmetry and meticulous repeatability, we move now from the manipulation of solid matter to the mastery of a subtler, flowing force, water under controlled pressure. Across the rugged mountains and fertile plains of ancient Persia, the Achaemenid Empire, spanning from 550 to 330 BC, developed hydraulic systems that channeled rivers, springs, and qanats through cities, gardens, and monumental complexes. Hidden within these networks were devices that regulated pressure, safeguarded conduits, and distributed water efficiently. The Persian hydraulic pressure regulators, remarkable for their subtlety and sophistication, yet almost invisible to the casual observer. Picture the palatial gardens of Persepolis, terraces cascading with greenery, fountains glinting under the sun, and channels of water flowing with serene precision. Within the stone and clay conduits, carefully placed regulators moderated the force of the water, ensuring that fountains maintained steady height, irrigation channels did not flood, and aqueducts could deliver a constant supply over vast distances. These were not simple valves or gates. They were mechanical intelligence embedded into the hydraulic infrastructure, designed to anticipate surges, accommodate fluctuations, and distribute energy without human intervention. Archaeological studies of Achaemenid waterworks reveal channels with subtle constrictions, chambers with graduated basins, and openings positioned to absorb or redirect pressure. Some structures suggest the presence of weighted or float-operated regulators, functioning as early feedback mechanisms. When water pressure increased, a movable element would rise or pivot, partially restricting flow. As pressure decreased, it would return to its resting position, restoring throughput. The design is elegant, efficient, and responsive, reflecting a conceptual understanding of fluid dynamics centuries before formalized theory. Mainstream explanations focus on practical necessity. The Persian heartland is arid, rainfall sporadic, and reliable water supply essential for agriculture, ritual, and urban life. Qanats, the gently sloping subterranean channels, required careful management to prevent overflow, erosion, or stagnation. Regulators ensured that water flowed evenly, even as source pressures fluctuated seasonally or daily. Yet the precision and consistency implied by surviving structures go beyond mere pragmatism. The spatial alignment of chambers, the sizing of inlets, and the integration of multiple regulators within a single network indicate deliberate planning and a systematic approach to flow management. Could the engineers of Persepolis have possessed empirical knowledge equivalent to what we now consider principles of pressure regulation? Experimental reconstructions provide a glimpse into the sophistication of these systems. When researchers attempt to replicate ancient qanats with simple weight or float-operated valves, the behavior is surprisingly predictable. Water flow can be maintained with minimal human adjustment, and sudden surges are absorbed and redistributed without destructive turbulence. Such functionality would have required careful calibration, determining the mass, buoyancy, and placement of regulating elements, adjusting chamber dimensions, and understanding how slight changes in slope or conduit diameter influence overall performance. The results suggest that Persian engineers possessed both intuition and method, applying observation and refinement to achieve consistent outcomes. Speculative interpretations expand the intrigue. Some scholars propose that these regulators may have served multiple purposes beyond flood control, balancing water between agricultural terraces, supplying ritual fountains with precise height and flow, or even creating visual effects in gardens and palaces. Could some have incorporated adjustable mechanisms for seasonal variation, anticipating fluctuations in supply and demand? Did Achaemenid hydraulic engineers share principles across the empire, standardizing valve design, flow ratios, and chamber dimensions across hundreds of kilometers of qanats and aqueducts? The surviving evidence hints at answers, but much remains hidden beneath centuries of sediment, erosion, and reconstruction. The materials and construction further reveal technological sophistication. Stone, clay, and metal components were integrated to withstand continuous water flow, resist erosion, and maintain mechanical function over decades. Some regulators feature smooth bearing surfaces for movable elements, while others incorporate stepped basins that dissipate energy gradually. The result is a system that simultaneously manipulates force, protects infrastructure, and enables predictable distribution, a subtle combination of engineering, material science, and observation. The cultural and practical implications are equally compelling. In an empire where cities stretched across deserts, mountains, and river valleys, reliable water supply was vital for agriculture, governance, and social stability. The ability to control flow with precision allowed gardens to flourish, ceremonial spaces to function as intended, and urban centers to grow without fear of unpredictable flooding. These regulators were not merely technical solutions. They were instruments of administration, power, and survival, enabling a civilization to harmonize with the unpredictable forces of nature. Yet, as with other ancient machines, mysteries remain. How exactly did Achaemenid engineers determine optimal regulator design? Were there written records, standardized templates, or oral traditions that guided construction? Or did each installation emerge through trial, observation, and iterative refinement? How many of these devices existed across the empire, and how consistent were they in function and design? Could more complex or hidden features, now lost, have extended their capabilities beyond what we can currently reconstruct? The archaeological record provides glimpses, yet much remains invisible, buried beneath sand, soil, and centuries of human activity. Standing before a surviving chamber or imagining water cascading through a qanat, one senses both simplicity and extraordinary sophistication. These systems, like the Indus microweights, Chinese casting molds, and Roman differential mills, demonstrate a consistent human impulse to measure, control, and harmonize forces with precision. The Persian hydraulic pressure regulators are not just valves. They are early analog computers, translating fluctuating energy into predictable, controlled outcomes, silently maintaining equilibrium across complex systems. And so, as we envision water flowing through subterranean channels, cascading into basins, and lifting weighted regulators into position, one question remains. How many other devices, hidden in stone and water, translated observation into control, balancing natural forces with near-perfect precision? How much knowledge of flow, pressure, and regulation has been lost to time, leaving only the surviving fragments to hint at the ingenuity of the engineers who created it? The Achaemenid hydraulic pressure regulators remind us once again that human innovation often lies concealed within subtlety, quietly orchestrating forces and achieving outcomes that continue to inspire awe thousands of years later. As the Achaemenid hydraulic pressure regulators fade from our imagination, fountains, qanats, and concealed mechanisms balancing water with subtle intelligence, we return to another ancient civilization whose mastery of moving water verges on the uncanny. In the bustling heart of the Roman Empire, where aqueducts carried crystal-clear streams over valleys, through tunnels, and across monumental arches, engineers developed devices that could measure the very flow of life itself. Lead and bronze aqueduct flow meters. These instruments, embedded discreetly within stone channels and metal conduits, allowed precise monitoring of water, ensuring equitable distribution across cities, public baths, fountains, and private estates. In a civilization defined by engineering prowess, these meters were both practical and extraordinary, a quiet testimony to Roman understanding of measurement, control, and regulation. Picture an aqueduct stretching across the Roman countryside, a ribbon of stone and masonry glinting under the midday sun. Water glides through smoothly plastered channels, its movement steady yet alive, responding to gradients, pressure, and seasonal fluctuations. Beneath bridges, inside distribution hubs, or within side channels, small bronze or lead devices monitor and guide the flow, capturing data in a form almost incomprehensible to us today. These are not decorative or symbolic objects. They are instruments of measurement, designed to quantify, regulate, and harmonize, a physical interface between human intention and the fluid dynamics of nature. Archaeological evidence from sites across the empire, most notably in Rome, Pompeii, and the villa complexes of southern Gaul, reveals small, calibrated apertures and bronze inserts embedded in lead conduits, sometimes accompanied by notches or markings. Scholars suggest these were used to measure flow rates, calculate volumetric supply, and detect deviations or blockages. Certain designs incorporate graduated steps or internal chambers that stabilize the flow, allowing for repeatable measurement without disturbing the channel's main function. In some instances, small float mechanisms or hinged gates may have provided dynamic feedback, adjusting passageways automatically to maintain consistent flow, a principle remarkably akin to modern hydrodynamic control. Mainstream interpretations emphasize administrative necessity. Rome was a city of over 1 million people at its height. Water was essential not only for drinking, but for public baths, fountains, latrines, and the maintenance of urban hygiene. Precise allocation of aqueduct water was critical, both for social stability and for legal enforcement. Municipal authorities maintained rigorous oversight, often assigning measured portions of flow to different districts or properties. Flow meters allowed engineers to verify claims, detect leaks, and monitor consumption, a system of accountability embedded directly into infrastructure. Yet the sophistication of these instruments often surpasses what simple municipal oversight would require. The precision evident in surviving examples suggests a deliberate pursuit of accuracy, reliability, and predictive control. Experimental reconstructions provide remarkable insight. Using bronze inserts in lead channels, researchers have replicated flow measurement with surprising fidelity. Gradual slopes, carefully sized apertures, and internal chambers create laminar flow conditions that allow consistent volumetric readings. Minor adjustments to the width or height of openings significantly influence flow, demonstrating that Roman engineers must have observed and refined these systems over decades, perhaps centuries, to achieve functional reliability. The integration of lead, a relatively malleable metal that could be precisely shaped and fitted, with bronze components, indicates both an understanding of material properties and an appreciation for durability under continuous hydraulic stress. Speculative interpretations expand the narrative. Could some meters have incorporated more advanced functions than simple measurement? Were they capable of providing real-time feedback, regulating branch channels automatically to maintain desired pressure, or even averaging flow over time through mechanical counters? Some scholars propose that certain bronze inserts, with curved internal channels or calibrated apertures, may have acted as early analog computers, converting the force and velocity of water into quantifiable, repeatable outputs. If true, these meters would exemplify an extraordinary synthesis of observation, mathematics, and mechanical intuition, an early form of engineering abstraction translated directly into functional infrastructure. The cultural and political context underscores the importance of these instruments. Control of water equated to control of power. Wealthy citizens, military garrisons, and public institutions all relied on measured water delivery, and disputes over access were common. Flow meters provided a level of impartiality, an objective measure of supply, independent of human perception or bias. They were instruments of justice, governance, and efficiency, embedded seamlessly into the empire's hydraulic network. At the same time, they reflect the Roman obsession with standardization, predictability, and quantification, a theme consistent across their roads, architecture, and mechanical devices. Material construction adds another layer of fascination. Bronze inserts, carefully cast or hammered, allowed precise shaping of internal channels, while lead conduits provided the flexibility to adjust fit and alignment. Some devices show evidence of polishing and finishing to reduce friction and prevent sediment accumulation. The combination of durable metals, precise geometry, and integration with flowing water demonstrates a level of craftsmanship that rivals many modern hydraulic systems. Every curve, taper, and notch reflects knowledge accumulated through trial, observation, and refinement, a tacit understanding of hydraulics encoded in metal. Yet, as with many ancient machines, profound mysteries persist. How widespread were these flow meters across the empire? Were there standardized designs, or did each installation vary according to local conditions, water pressure, or municipal priorities? How did Roman engineers calibrate devices without formal measurement tools in the modern sense? And how was knowledge transmitted across regions spanning hundreds of kilometers? Were there additional functions now lost to time, perhaps hidden in bronze levers, floats, or even inscriptions we have yet to interpret? The surviving artifacts hint at answers, but the broader network of hydraulic intelligence remains partially obscured by centuries of decay and reconstruction. Standing beside a reconstructed flow meter, or visualizing water coursing through lead and bronze conduits, one senses the same quiet mastery evident in other ancient machines. The Indus microweights, Chinese casting molds, Persian hydraulic regulators, and Roman differential mills. Each represents the human drive to understand, predict, and control forces that are otherwise invisible or variable, forces of water, gravity, or motion, translated into tangible mechanisms. The flow meters were not mere instruments. They were interfaces between human intention and nature, mediating complexity with subtle precision. And so, as we imagine Roman aqueducts carrying millions of liters of water daily, and as bronze and lead meters silently gauge, regulate, and measure, one question lingers. How many other systems of precision, hidden in stone, metal, or flowing water, remain undiscovered across the ancient world? How many devices, designed to quantify and control forces with near-perfect accuracy, were lost, dismantled, or forgotten, leaving only tantalizing traces for modern eyes to decipher? The Roman lead-bronze flow meters remind us once again that human ingenuity has long sought to master the unseen, embedding intelligence into the very infrastructure that sustains life, even when that intelligence remains invisible to all but the most attentive observer. As the Roman lead-bronze aqueduct flow meters fade from memory, silent, meticulous guardians of water, quantifying and regulating the lifeblood of cities, we return once more to the heart of the Yellow River Basin, to a period when fire and air were the twin agents of transformation. During the Han Dynasty, between 206 BC and 220 AD, China saw the rise of a remarkable metallurgical culture, one in which human ingenuity intersected with elemental forces in ways that border on the imperceptible. Central to this mastery were the bellows, devices that channeled air into furnaces to raise temperatures with astonishing control. And yet, the true marvel of Han metallurgy lies not in the bellows themselves, but in the valves integrated into their systems. Small, often overlooked mechanisms that regulated airflow with precision, subtlety, and a consistency that continues to astound modern researchers. Imagine entering a Han Dynasty foundry at dawn. The first rays of sunlight filter through latticed windows, illuminating plumes of smoke that rise lazily from clay furnaces. Workers kneel by bellows, adjusting leather flaps and wooden levers as molten metal glows in crucibles. A faint hiss escapes from each bellows, a sound almost imperceptible to the untrained ear. But within that whisper lies a miracle of control. These valves, meticulously carved and fitted, govern the velocity and pressure of air reaching the fire. Too little air, and the furnace languishes. Too much, and the bronze or iron could overheat, warp, or fracture. In these small components, the Han metallurgists encoded a mastery of airflow and thermal energy that rivals the precision of mechanisms in distant civilizations we have explored, from the Roman mills to Persian hydraulic regulators. Archaeological fragments and textual evidence hint at the sophistication of these devices. Excavations of Han-era workshops have yielded fragments of bellows and copper or bronze fittings that suggest movable valves, possibly hinged or counterweighted, capable of adjusting airflow in response to changing pressure. Contemporary texts, including the later Tiangong Kaiwu, describe methods for regulating furnace combustion, indicating awareness of the relationship between airflow, temperature, and alloy quality. Some valves appear to have been designed for automatic responsiveness. When pressure rises too high, the valve opens slightly, releasing excess air. When pressure falls, it returns to a closed or partially closed position. The implications are striking. Han artisans may have engineered rudimentary feedback systems, anticipating outcomes without the aid of written formulas, thermometers, or modern gauges. Experimental reconstructions provide further insight into the sophistication of these systems. Researchers attempting to replicate Han bellows with weighted or hinged valves have found that minor adjustments in mass, lever length, or hinge tension dramatically affect the consistency of airflow. Maintaining a stable furnace temperature requires not only careful control of fuel and bellows motion, but also an intimate understanding of the valve's dynamics. Achieving repeatable results, as Han metallurgists evidently did, would have demanded extensive observation, iterative refinement, and possibly the transmission of empirical knowledge across generations. It is easy to imagine apprentices watching a master, feeling the subtle resistance in a valve, and learning how to reproduce the same precise effect hundreds of times over. Mainstream explanations frame these valves in the context of practical necessity. Furnaces must reach and sustain high temperatures to melt bronze, refine iron, or cast delicate ritual objects. Inconsistent airflow could ruin a casting, weaken a tool, or deform a ceremonial vessel. Yet the precision evidenced in surviving artifacts often surpasses the demands of ordinary metallurgy. Some valves are small, almost delicate, yet exhibit careful calibration that allows a consistent flow even as bellows are operated unevenly by different workers. Could this reflect an understanding of early principles of control theory, a mechanical intuition that converts observation into predictable outcomes? If so, it suggests that Han engineers were not only skilled artisans, but also proto-scientists, experimenting with variables and developing techniques that allowed forces of fire and air to be tamed reliably. Speculative interpretations invite even deeper reflection. Were these valves purely functional, or did they embody a conceptual understanding of airflow as an energy to be measured, modulated, and balanced? Could certain designs have allowed for adjustable regulation, enabling operators to vary temperature according to the demands of different alloys or casting forms? Some scholars speculate that Han metallurgists may have developed standardized valve designs, ensuring consistent furnace operation across workshops and even across provinces, a technological uniformity echoing the standardization seen in Indus microweights or Roman aqueduct systems. The precision suggests not only technical skill, but a cognitive leap. The translation of observation, material behavior, and human intent into physical systems capable of repeatable, reliable outcomes. The cultural context of these devices further deepens their intrigue. Metal was more than a material. It was power, status, and ritual significance. Weapons needed strength and balance. Tools required durability and accuracy. Ceremonial vessels demanded symmetry and flawless surfaces. A furnace operating with unpredictable airflow could compromise both function and symbolic meaning. The valves, then, were more than mechanisms. They were guarantors of quality, ensuring that each piece emerging from the crucible met exacting standards. They mediated a complex interplay between human intention and natural forces, a quiet but essential link in the chain from raw ore to finished object. Material considerations underscore the ingenuity involved. Valves were constructed from bronze, copper, or wood, carefully fitted into leather or clay bellows. Surfaces were polished to minimize friction, hinges counterbalanced for smooth operation, and apertures carved to exact dimensions. The combination of pliable materials like leather with rigid metals like bronze allowed subtle calibration, enabling valves to respond dynamically to pressure changes. Each component required an intimate understanding of material properties, as well as an appreciation for wear, expansion, and resilience under repeated heating. The Han metallurgist's ability to integrate these elements into functioning systems reflects a sophistication that is rarely acknowledged outside specialized studies of ancient technology. As with other ancient machines, the questions that remain are as compelling as the evidence itself. How were these valves standardized, if at all, across workshops in distant provinces? Were there shared principles, templates, or measurement standards guiding their production? Or did each artisan develop solutions independently? How did operators calibrate them without modern instruments? And how was knowledge transmitted between master and apprentice? Could there have been additional, now lost mechanisms, hidden levers, float-activated regulators, or subtle interlocks that extended the valve's capabilities? The surviving fragments provide tantalizing clues, yet the broader understanding of Han metallurgical control systems remains largely concealed, obscured by time and the perishable materials used in their construction. Standing before a reconstructed bellows or imagining the operation of one within a furnace, it becomes clear that the Han valves embody the same impulse for control, measurement, and precision evident in other ancient machines we have explored, from Indus micro-calibrated weights to Persian hydraulic regulators, Roman mills, and lead-bronze aqueduct meters. They translate abstract understanding into physical action, subtle forces of air modulated to achieve consistent results, human intention embedded into a system of repeated performance. The valves are not just tools. They are interfaces between cognition, material, and elemental force, quietly ensuring that fire and air yield predictable, repeatable outcomes. And so, as the bellows are pumped, air surges through the valves, feeding the glowing crucible and tempering molten bronze with silent precision. One question lingers: how many other ancient systems, hidden in leather, bronze, and wood, translated observation into control, creating reliable outcomes from variable forces? How much empirical knowledge, encoded in mechanism and process, has been lost to time, leaving only fragments and traces for us to decipher? The Han Dynasty precision metallurgical bellows valves remind us that the pursuit of accuracy, whether in fire, water, air, or metal, has always been a defining aspect of human ingenuity, an invisible thread connecting civilizations across continents and millennia. As the Han Dynasty bellows valves fade into memory, the subtle mechanisms that modulated fire and air to create consistent, high-quality metalwork, we travel far across continents and centuries, from the crucibles of ancient China to the towering stone cities of the Andean highlands. Here, between jagged mountain ridges and cloud-kissed valleys, the Inca civilization, between roughly 1438 and 1533 AD, achieved feats of engineering that remain astonishing in their precision, subtlety, and enduring resilience. Among their many innovations were the enigmatic stone sliding gate mechanisms, massive blocks, often weighing tons, yet designed to move smoothly within perfectly aligned channels, functioning as gates, access controls, and possibly even regulatory devices within sacred or administrative complexes. These mechanisms, hidden in plain sight, reveal a sophistication that invites both admiration and wonder, echoing the precision seen in the Han bellows, Roman aqueduct meters, and Persian hydraulic regulators we have explored. Imagine standing at the edge of Machu Picchu or Sacsayhuaman at sunrise. Mist curls around terraces and ramparts, and the first light glances off walls of precisely cut stone, each block fitted to its neighbor with astonishing accuracy, sometimes so tight that a knife cannot slip between them. Within these walls, some blocks are not fixed. They are mobile, sliding within carefully carved channels or grooves. A massive slab, aligned with near-atomic level precision, moves smoothly under applied force, pivoting or sliding to open a doorway or seal a chamber. The motion is subtle, yet the implications are immense. It represents control over enormous masses with minimal effort, the translation of geometry into mechanical function, and the deliberate design of systems that endure for centuries without lubrication, metal fasteners, or modern technology. Archaeological investigations have revealed numerous examples of these sliding stone gates across Inca sites. Some appear within fortress complexes, others within ceremonial centers, and a few are positioned near water channels or storage rooms. The blocks are typically hewn from granite or andesite, carved with such precision that their channels or rails provide near frictionless guidance for sliding. The degree of straightness, smoothness, and alignment is extraordinary, considering the tools available to Inca stonemasons: chisels of harder stone, bronze implements, and wooden levers. The engineering is so refined that the gates could be opened or closed by only a few individuals, even when the stones weigh several tons, hinting at an understanding of leverage, balance, and friction that borders on intuitive physics. Mainstream explanations emphasize practicality. Sliding gates provided security, controlled access to sacred or administrative spaces, or protected storage rooms for grain, ritual items, or water. Their precision ensured that the gates operated reliably, preventing accidental jamming and maintaining structural integrity within walls that had to withstand earthquakes, a recurring threat in the Andean region. Some scholars suggest that the gates may also have served to channel energy, guide ceremonial processions, or convey social authority through controlled access. Yet these explanations only scratch the surface of the mystery. The degree of precision, the subtle use of gravity and balance, and the apparent universality of the mechanism across multiple sites suggest a deeper, almost systemic knowledge of mechanics and material behavior. Experimental reconstructions of Inca stone sliding gates have illuminated some of this sophistication. By shaping stones with near-perfect parallelism, engineers of today can reproduce the low-friction movement observed in archaeological examples. Even when blocks weigh several tons, slight angles in the channels, the precise orientation of contact surfaces, and careful management of force vectors allow motion with minimal human effort. Could Inca engineers have understood, even intuitively, principles of load distribution, center of mass, and friction optimization? The evidence suggests they did, yet the transmission of this knowledge, whether through apprenticeships, oral tradition, or ceremonial instruction, remains largely undocumented. Speculative theories expand the intrigue. Some researchers propose that sliding gates may have incorporated subtle feedback systems or alignment checks. Could the grooves themselves have functioned as guides that ensured structural adjustments during earthquakes, allowing gates to shift slightly and avoid catastrophic damage? Might the design of the gate and its channel have allowed water, airflow, or even light to pass in controlled patterns, subtly regulating environmental conditions within ceremonial or storage spaces? There are even hypotheses that sliding gates could have been used as part of astronomical observations or timekeeping, aligning with sunlight or shadows during solstices, thus serving dual purposes: mechanical function and cosmological calibration. While concrete evidence for such functions is limited, the precision of the mechanisms suggests that they were conceived with intentionality and versatility. The Inca mastery of stone and geometry is central to the intrigue. Unlike many civilizations, the Inca lacked widespread use of mortar. Their constructions relied on dry-fitting stones with incredible precision. The sliding gate mechanisms exemplify this mastery, requiring absolute accuracy in both the block and the channel. Minor deviations could render a gate immovable or compromise structural stability. This implies not only observational skill but iterative engineering, trials and refinements, perhaps over generations, to perfect the fit and function. The precision is so high that it has often been compared to modern machining, yet it was achieved with chisels, hammerstones, and wooden levers. The material choices further underscore the sophistication. Hard granites and andesites were quarried, transported, and dressed with remarkable care. Surfaces that guide sliding blocks were polished or leveled to reduce friction and prevent wear. Levers and ropes of natural fibers were likely used to move the blocks, but their effectiveness depended entirely on the precision of the stonework. This suggests a holistic understanding of mechanical systems, where material, geometry, and applied force are considered together to produce repeatable, controlled motion. Cultural context is equally compelling. Sliding stone gates controlled access to palaces, temples, and storage facilities, regulating human movement. protecting sacred or valuable objects, and, perhaps, mediating ceremonial experience. Their placement within urban and ceremonial planning implies that mechanics were deeply intertwined with governance, ritual, and symbolic authority. To open or close a gate was not merely a physical act, but a deliberate manipulation of space, movement, and perhaps even perception. The interplay between human action and massive stone elements, guided by precise channels, may have conveyed power, mastery, and harmony with the natural environment. Yet, as with other ancient machines, profound mysteries remain. How did Inca engineers achieve such extraordinary precision without written measurement systems, standardized tools, or modern surveying instruments? Were there hidden techniques, lost to time, that allowed them to measure and cut granite to near-perfect tolerances? How many of these gates were once operational, and how might their function have extended beyond mere security or access control? Could there have been integrated mechanisms, now vanished, that allowed these stones to serve dual purposes in environmental regulation, ritual, or even communication across complex sites? The surviving examples tantalize the imagination but provide only partial insight. Standing beside a massive sliding block or visualizing one gliding smoothly within its channel, one senses the same impulse toward precision that runs through the history of ancient machines. From Indus micro-calibrated weights to Han metallurgical bellows valves, Roman flow meters, and Persian hydraulic regulators, human ingenuity repeatedly reveals a drive to measure, control, and harmonize forces with extraordinary subtlety. The Inca sliding gates are another expression of this impulse, a testament to mechanical understanding, material mastery, and the translation of observation into repeatable, functional outcomes. And so, as the Andean wind brushes across terraces and stone ramparts, as the sunlight shifts along perfectly cut grooves, one question persists. How many other mechanisms, hidden within the architecture of ancient civilizations, translated observation, intuition, and skill into precise control of matter and force? How much knowledge, encoded in stone, bronze, and other enduring materials, has been lost to time, leaving only tantalizing fragments to hint at the ingenuity of our ancestors? The Inca stone sliding gate mechanisms remind us that precision is not merely a feature of machines. It is a thread woven through the history of human creativity, bridging continents, technologies, and millennia, and whispering of systems yet to be fully understood.